for people to join in, and we'll get started at 1 o'clock.
What if I'm not ready?
Your slides are going to be on the screen.
Okay. I'm just going to be silent the whole slide.
Excellent, excellent. The virtual, I think so far the virtual honor or the virtual symposium is working out quite well. We have good turnout. Poster presentations this morning were excellent. A lot of good questions, a lot of good research. So so far it's been a typically wonderful best day on campus.
Best?
Oh,
Are
yeah.
you okay?
This is the best day on campus.
Well, this is way better than my ACS presentations. I will not complain.
Graduation's all right too.
Yeah, graduation's pretty good too. Well, graduation is sad for us. We get to lose our great seniors. And
I know, you're gonna miss me so much.
They go on to do wonderful things. So. All right, my clock says 1 o'clock, and so I think we should get started. Good afternoon, everyone. Welcome to the 31st Annual Elkin Isaac Research Symposium. This is forum number 3. We have a lot of chemistry, a couple math talks in our session this afternoon. My name is Craig Beeler. I'll be the host for this afternoon's presentations. Mike Van Houten is going to be moderating the questions at the end of each talk. The way it's going to work, what I'm going to do is introduce each speaker. They will give a 12, 13-minute presentation, and then we'll have time, a couple minutes after their presentations, to allow for questions. If you have any questions, please place those questions in the chat, and Mike will read those off for our presenter. So without further ado, I want to get started. So our first presentation is by Clara Wagner. Clara's faculty sponsor is Dr. Craig Strew.
Hi, I'm Clara Wagner. Thank you for the introduction, Dr. Beeler. My project that I've been working on in the Strew Chemistry Research Lab has been working on synthesizing a photoswitchable cancer drug. You can go to the next slide. So normal cells work where they replicate itself and they make copies. And then when there's cell damage and they can't repair it and the cell can't figure out a way to correct the mistake, it goes into apoptosis or cell suicide. But when cells continuously do this and don't catch their mistake, the mutations can build up upon itself and create uncontrolled growth, known commonly as cancer. Many people have been either affected by cancer or know someone that has cancer or has a friend or a close relative that has been affected by cancer. So this idea is really important to a lot of people and close to my heart as well. You can go to the next slide. So here I'm talking about my cancer target. And so when the cell cycle happens, the cell replicates and then divides. So to the right, you can see the chromosomes coming together, replicating, and then pulling apart. So the thing that pulls them apart is called tubulin, and that is what I focus on in my project to prevent the tubulin from pulling apart and then causing like cell death, essentially. And so that's the target that I've been focused on. We can go to the next slide. So this is kind of how drugs work. The drugs will bind like a lock and key, and it will bind into a specific shape. So as you can see, like different keys can fit into a lock. Sometimes this can be a problem because you can have certain keys that fit into the wrong locks and turn on and off different things that you don't want to turn on and off. But this is why making drugs that are really specific is really important. So it will stop the protein from binding and then therefore will stop cell replication. We can go to the next slide. So my favorite part about like working in the Stru lab is that we get to work with Azo Compounds. So they originally came from textiles actually, and they're used for like really vibrant colors, and they're really commonly found in like foods and different things like that. So if you're ever curious if you have like a vibrant food, you can look up if it has like an azo in it or a textile and see if it has azos in it. But they're a nitrogen-nitrogen double bond, and you can actually activate them and change the shape of the drug by shining different wavelengths of light onto the drug for a certain amount of time, and then it will actually flip back sometimes. So we apply this concept to the cancer drugs, and we're able to make a really interesting type of cancer drug. We can go to the next slide. So all the drugs in the Stru group use this concept where we have the regular drug, which is the red dots on the left side, where that's like how a normal cancer drug would work. It's active in the entire body. You have to have lower dosages of the drug so that it doesn't hurt healthy cells, but is still effective for the rest of the like body. But what's really cool with our drugs is we can actually give a patient an inactive drug and then shine a light in the area that we want it to be active in and only activate the drugs in that area so that we get really specific cancer drugs. And this will decrease symptoms like hair loss, nausea, and like weight loss and other bad things that happen when you're going through cancer treatment. So that's some really great advantages to making drugs that aren't active everywhere in the body. We can go to the next slide. So some of the previous work that was done by Dr. Stru is they used a plant, like a African willow bush, and they take this drug, and basically here it's like explaining that they were able to make a photoactive cancer drug, and then they tested it with cells, and as you can see on like the right side, he tested it with certain wavelengths of light, and you can actually see the dead cells versus the living cells and the comparison once the light was active on the drug itself and how it killed the cancer cells there. So it's like it's a really important way to kill cancer cells and build off of this work and show that it is possible to make drugs that can kill cancer cells using light. So that was really impressive. We can go to the next slide. So making drugs is kind of like building the Great Pyramids. You kind of have to use everyone's previous work and use what they found out, whether it was like a failed or a success, and apply that to your own work. And everyone this is all in science and every really study ever, that you have to help each other and share information and, get the next brick up to the pyramid so you can have a massive pyramid and make it a wonder of the world. But a really great advantage to kind of using past work and like looking at past work is that it saves a lot of time in the drug discovery process, which is really a timely process and an expensive process. So if we can skip a few steps and figure out what works and what doesn't work, it's really important to record your work and keep a good lab notebook. We can go to the next slide. So to the left is the proposed synthesis that I worked on for the tubulin drug, and to the right is kind of what I'm currently working on. I just kind of wanted to put it on this slide because it is what I'm currently working on, but I probably won't touch on it too much. But to the left is a different synthesis that I ran in the lab to make the target drug, which would be, it's the very last, yeah, right there. Thank you, Dr. Bueller. It's the very last drug that is my target. So each synthesis, you can see that it's the same one. As you go down, there's just different possible ways to get there. So if it doesn't work, I just go to the next one. Yeah, thank you, Dr. Bueller. You can go to the next slide. So this is kind of what I do in the lab each day and what I've done during the summertime when I had FIRSCA. So I would run a reaction, but before you even run a reaction, you have to read the papers, weigh out your materials, find your chemicals in the lab, which I know many know how difficult that can be within itself, and dry your glassware, make sure your glassware is clean, and then run your reaction. This is one of my favorite reactions to run because it looks really cool, but it's pretty simple. And then, so I usually run a reaction, take notes, observe what's happening, and then I extract the aqueous. So I separate the different layers to really get what I want out of it. And then I do a TLC, or a thin layer chromatography, where you can see like the starting material, and then, yeah, and then that one would be like the stuff that I don't want, and at the top is the stuff that moved upwards. So that means I've created something different than the start, which is a really good thing. And then I usually do flash chromatography. So this is a lengthy process that a lot of chemists don't like to do because it takes so long. But that's why it's nice to have good lab group friends, because they encourage you through this process. So that takes a while, and then I separate them out and I combine the samples that I want into a round bottom flask and run it on the big, there's like a room in the science center where we run it on the NMR, and it gives us a nice pretty graph usually. We can go to the next slide. So this is the results of the synthesis that I've done. So these were usually run like twice to make sure they didn't work if they didn't work. So as you can see, the Mills coupling was unsuccessful. There's some theories of why this happened, but I won't go too deep into that. The Diazonium Salt was actually, we were pretty excited about that because 2 of those steps worked, and then when we put them together, they did not work. And then the last step I didn't add, but this very last step did not work either for the last Diazonium Salt. But then my new synthesis that I'm currently working on, that one's looking very hopeful for a different target and a different drug. So I'm pretty happy about that. That will hopefully happen soon before I graduate, and I'll be able to finish that. We can go to the next slide. I'd like to acknowledge Dr. Strew for letting me do research in his lab and always being around to ask plenty of questions. Dave for constantly being a major help, always asking us how we're doing, checking on us, even though he doesn't have to. The chemistry department, FIRSCA, the Student Research Partners Program that sponsored me like my freshman and sophomore year. It was a really amazing experience that they let me have at Albion. The lab crew that constantly keeps my spirits up and, you know, keeping a positive attitude even when things don't work in the lab. Dr. McCaffrey and Renee for the honors program. We used to have a Tuesday journal club pre-COVID with Dr. Rollman. Dr. Cliff Harris for teaching me really interesting lab skills. I've really appreciated that through his classes and different research different like scientific techniques, and Dr. Rollman. We go to the next slide. Thank you so much for coming to my talk. I hope you were able to learn something new. And if anyone has any questions, let me know.
Please enter questions into the chat. Okay, we have our first question. Can you talk more about the new drug you will work with?
Yeah, I can. So the new drug that I'm working with has to do with it's also related to cancer, and it was given to me because a different student was interested in a different project. So I'm more focused on the synthesis of that drug, but it essentially has the same goal that this project has with just like creating a photoswitchable drug. But I really like the new project because I get to work with super low temperatures, and it's really challenging. So it it forces me to think outside the box in many different ways. So I get to use pretty cool different techniques that I've been learning more about. So I really like the new project.
And I think we can fit in one more question, which was, which synthetic step was the most difficult?
Great question. It depends on the day and how much time I have in the lab. And just like, usually I try to have a really good attitude, but sometimes that affects a science as well, as I'm sure many of my chemistry friends also could talk about that with. But I would say that I don't really look at it as like a difficulty. I look at it more as like an opportunity to learn more, I guess, as cheesy as that might sound, to try and force myself to keep going and keep trying new and different things, which thankfully Stu has let me do over and over again, even if we're unsure that it would work at all. But I'd say it's not really difficult. I find it more fun. So thank you for all the questions and for coming, everyone. I really appreciate it.
Great. Thank you very much, Clara. Wonderful presentation. Lots of applause I heard in the background. Okay, we can move on to our next presentation. Our next presentation will be given by San Pham, and Dr. Craig Strew is her faculty advisor. San.
All right. Hello, everyone. My name is San Pham. I've been working with Dr. Strew for the last 4 years, and today I'm going to talk about the synthesis and characterization of Azole C-kit and Type 2 inhibitors for light control cancer treatment, and also to add on to Clara's about the difficult step. If it's hard, if it's failed, it was difficult. So, no sugarcoating. Next, please. All right. So as you already heard, so our group is interested in creating cancer drugs, and like especially novel cancer drug with Azo Compounds. So my project also related to that, but also with some added feature. So in the figure on the left is how cancer spread throughout the body. So if you look at the blob, the orange blob on the top of the figures. Is the cancer growth caused by uncontrolled cell division, and as it grows, it later gained the ability to hijack the body blood vessel and spread throughout the body to other places, which also known as metastasis. But and then for an example of that is on the figure on the right. If you look at the breast cancer or melanoma skin cancer and follow the red arrow, you can see that these cancer can spread to become brain metastasis or brain cancer over time. And next, please. And the reason for that is, through tumor angiogenesis, also known as blood vessel formation. So in normal cell, that is a normal occurrence because cell require energy, nutrient and oxygen in order to grow. So they need the blood vessel to carry off that. As for cancer cell, they grow even faster, so they require much more nutrient and energy and oxygen. So they basically reroute the vascular system to themselves in order to get all the nutrient. So if you look at the bee panel B, you can see that the tumor blood vessel is abnormally large and interwoven in between the cells, and later they can gain access into the into the vascular system for metastasis through these blood vessels. Next, please. So in order to stop both uncontrolled cell growth and angiogenesis, we decide to create two drugs for two targets, as shown here, the c-KIT and Tie2 kinases. So kinases are proteins that are responsible for important cell function as cell division and cell growth. So in this slide are the two figures that show how c-KIT and Tie2 can cause cancer. So on the figure on the left is for c-KIT. So on the left side of the figures is the normal c-KIT, which is the green figure, the green stick, which require the binding of a ligand in order to initiate cell growth and division. However, when it becomes mutated, it can be activated all the time without any ligand binding. So as you and that's caused uncontrolled cell growth. And on the figure on the right is how Tie2 is implicated in tumor angiogenesis. So cancer cells, they have the ability to produce their own signaling molecules that basically tell the body to produce blood vessel for them. So that's how Tie2 is implicated, as Tie2 is one of the blood vessel formation kinases. Next, please. And there has been many drugs that been produced for c-KIT and Tie2 kinases, and as Clara will talk about, our group is interested in improving on known drugs, which save time, and of course, it has already known properties. So the figure on the left show c-KIT inhibitor and Tie2 inhibitor. So the top one is c-KIT and the bottom one is Tie2. I also include the IC50 values, which show how good a drug is. So the lower the values is, the better the drugs. So these two drugs both have really good values for inhibitors. However, they also accompany with lack of specificity and selectivity, because even though the drug is really good, it's hard to design a drug that would only attack one single target and not the other. So as a result, it causes a bunch of side effects. So we think that there's a lot of room for improvement. Next, please. And then, as you already know, our group focus on making Azole Compound, which is nitrogen double bond compound that can switch shape from trans to cis and cis to trans based on specific wavelength of light. And as drug work in the lock and key mechanism, it's good to be able to control the drug. So if you look at the receptor, it can bind only one single conformation, and in this case, the trans conformation. And if we can control the shape with light, we basically turn the drug on and off with light. Next, please. Which leads us to the light-sensitive therapy scheme here, as where we can introduce an inactive form of a drug in the body, and it would not cause any side effects. But then when we shine light on a specific tumor area, only that area will be activated, and only the drug in that part will cause damage to the cell. So we can reduce a lot of side effects with this localized activation. Next. And here's the typical workflow of the STRU lab before I go into my my research. So first we have to design, and then we have to synthesize these drugs, and these usually can take up to months or years. It depends on how difficult the drug is. And then we can test the drug ability to switch shape with light with UV vis and NMR spectroscopy in the middle two panels. And then finally, after that, we can figure out how to test the biological activity of these drugs in the last panel using in vitro assay and in vivo and stuff like that. Next, please. So for my first project is for c-KIT. Click next, please. So we basically replaced the amide bond that was highlighted in the in the in the red circle with the azo bond. Next, please. And I was able to synthesize this drug 2 summers ago. And here's are the steps with the use for each step. Overall, this drug has a 1% overall yield. And it took quite a while for me to get this, but it worked. So I was happy. Next. And then I was able to test its ability to switch shape with light. So this graph has a lot of information, but I walk you through. So the blue and the green line represent the trans conformation of SP057. Click, please. And then the yellow represent the cis conformation. Click, please. And then the green line represent the drug when it's not irradiated with any light. So we can conclude that the drug predominates in the trans conformation when there's no light. And then click, please. With strain for 65 nanometer, after 5 seconds, the trans conformation go to cis conformation. And click once again, please. And then the cis go back to trans with 465 nanometer wavelength after 10 seconds. And I was able to show that the drug can switch back and forth multiple times without degrading, as I was able to repeat this switching cycle multiple times. Next, please. And then after I gained the information for like how good it is, I mean how stable it is against light exposure and what wavelength it works with, it's good. It's important for us to know like how long the drug can stay in one conformation compared to the other. And the conformation that we focus on is the cis conformation, because when we go from trans to cis, the cis conformation will not stay in that conformation forever. Instead, it will slowly revert back to the trans conformation over time in the dark. So here's the graph that show that. So the green line is the no irradiation drug, which is in the trans conformation, and we switch it to cis conformation, which is yellow line, and I let it incubate in the dark at room temperature for 74 hours, and it showed like basically no sign of switching back to the trans conformation, which is extremely exciting and unusual for this type of Azo compounds. But it doesn't mean that my drug was degraded or anything, because after I hit it with 465 nanometer light, it revert back to the trans conformation, which show that the cis conformation is extremely stable at room temperature. Next. And then I was able to do modeling in order to figure out what shape will be the key for the binding pocket of the c-kit. So as you can see in the figures, using computational modeling, I found out that the trans conformation fit into the pocket. Click, please. And then if you look if this is another representation of a drug, in the green blob fit really snugly into the binding pocket like a key in a lock. Next. And then I also tried to figure out if the cis can bind, and it clearly cannot. As you can see, the thing in the drug in the red circle cannot bind. Next. And then I also did the same thing for SBB033, which is my Tie2, Azole Tie2 inhibitors. And I also switched that Azo bond switch that amide bond to the Azo bond. And then I also have to come up with a new synthetic scheme. So they had c-kit and Tie2 inhibitors both share similar features. So I thought I could use like the common fragment that I already know how to synthesize from c-kit for Tie2, and then add one more step in order to finish the synthesis, but it didn't work. So I have to change everything. Next, please. And I actually got it to work. Thank goodness. And it relatively high yield, which is exciting for us. Next. There you go. And then I also were able to test the photoswitchability of SBB033. So the trans conformation can switch to the cis conformation with 365 nanometer light after 1 minute. and the reverse shape change take 465 nanometer light after 1 minute. And I was able to show that it can switch back and forth multiple times too. Next. And then molecular modeling showed that the trans conformation of SBB033 is the key for this Ty2 kinase. And if you look on the figure on the right, the blob, the blue blob show that it fit really tightly into this binding pocket, which is really promising for our biological testing. Next. So for future work, I want to finish characterizing the photophysical properties of both drugs, and I want to finish the biological activity of uh, their biological activity testing, and then I want to publish those results in journal articles. Next. And I would like to thank Dr. Strew, Dave Carey for all the things that they did in lab, Dr. McCaffrey, Renee, and Fusca for running the program and allow me to do this research. My fellow lab mates, especially the people in the parentheses, and the Albion College Chemistry Department. Next. And I would like to thank you for listening and look at the meme, please. I like it a lot. And that's all I have.
I think we may have time for one question if anyone has one. And here's a question. Come back. Why is it still so hard to starve these cells so that they can no longer reproduce?
Oh, to starve these cells? Well, cancer cells I think are pretty smart. They have like mutation, and and then they are able to like um, produce different like features after every generation of cells in order to overcome whatever um, I don't know, whatever difficulty we present to it. So even if we try to starve the cells, as you can see, they will have their own signaling molecules and build their own blood vessel system to feed them. So I don't know. We'll see if we're gonna figure it out.
All right. Thank you very much, San. Wonderful presentation. Thanks and congratulations. Let's move on to our next presentation. Our next presenter is Noah Robertson, and Noah's faculty sponsor is Dr. Craig Strew. Noah.
Can y'all hear me all right? Cool. So yeah, thanks everyone for coming. I hope everyone's having a good time so far. Claire and San, those are two tough acts for me to follow, but I'll do my best. All right, go to the next slide. So the first thing I want to do is introduce our immune system. It's been keeping us alive, and typically when we think of our immune system, we think about its way to defend us against pathogens like parasites or bacteria or coronaviruses. Can you click? But what we don't give it enough credit for is its defense against cancer. So the reality is there's a good chance that all of our bodies have had cancer cells in them at some point. It's just that our immune system's been good enough to detect them and take them out before they start growing uncontrollably. Next slide. One of the ways that this happens is through immune checkpoints. So you can look at immune checkpoints as either brake pedals or gas pedals for the immune system. So when that gas pedal is depressed, your T cells are going to be active, or when you push down that brake pedal, they're going to be exhausted. Can you go to the next slide? So that's kind of the basis behind immunotherapy. It's manipulating our own immune system to help fight off diseases for us. So one immune checkpoint of interest would be PD-1, PD-L1. So this stands for programmed cell death protein. So PD-1 is expressed on your immune system, or your T cells here. And that kind of just, as your T cells patrol around your body, PD-1 will link up with PD-L1. And that's kind of a way for your immune system to know that this cell belongs in the body. It's one of the brake pedals. So linking up PD-1 and PD-L1, that's a brake pedal. The problem is cancer sees in its tumor microenvironment, it sees other cells presenting PD-L1. So it starts to do the same. And that way, cancer can present PD-L1 as a way to evade the immune system. You know, the next slide. So there are drugs already out there that do a great job at blocking this interaction. So they're monoclonal antibodies, and one of them is called nivolumab. It's a PD-1 inhibitor. The issue is that, you know, it's a biological drug. It's a huge protein. It's not something that we can make, you know, every day upstairs in the labs here at Albion. You know, they have a huge molar mass, and they're really expensive. That's the issue. So if you tried to take this drug orally, it'd be the world's most expensive protein shake. You know, there's a lot of logistical implications here. You know, you need to take your relative to like an infusion clinic or to the hospital, and then you're not only paying for the cost of the drug, but, you know, you're paying for the people who have to administer the drug. They have to monitor it. So next slide. So on the left is a ribbon structure of PD-1 and nivolumab. So nivolumab, which is the drug, it literally just sits on top of PD-1. So when it's bound to PD-1, there's no way that PD-L1 can get in there and make that interaction. Can you click 3 times? So we want to make a small molecule as opposed to a protein. So this isn't even to scale. Our small molecule is going to be way, way, way smaller than nivolumab. But the reason we want to make a small molecule is so we can have something that has, you know, it can be administered orally or it have a better shelf life. But really, it's just something that we can make upstairs in our chemistry labs. Next slide. So Bristol Myers Squibb's already had this idea before us. So they designed all these drug candidates, and they're all centered around this core scaffold here in the middle. But the problem is that these drugs, they were found to be a little too cytotoxic. Next slide. And the reason that they're cytotoxic is because, well, it's the shape and the chemical properties of the drug. So you can think of drugs and how they work like a lock and a key. So instead of targeting PD-1, BMS targeted PD-L1. So PD-L1 is going to be their lock, and their drug, I guess in this case it'd be 1166, it's going to be the key. When they introduce their drug to PD-L1, 2 PD-L1 proteins will come together and it forms a homodimer. So it's basically 2 of these proteins sandwiched together. And when that happens, the binding interfaces are blocked off, and the protein's so big it can't interact with PD-1. Can you go to the next slide? So the reason we want to do this, the way we want to make it our own is by making it into an azo molecule. Can you click next? So azo molecules have a nitrogen-nitrogen double bond between 2 aromatic rings. One cool property about these chemicals is that they have very vibrant colors. They're oftentimes used in dyes, but that's not really why we're interested in them. You can go next. What we're looking for here is the photoswitchable properties of these azo molecules. So on the left is BMS 37, and combining the left and right hemisphere of the molecule, they have a carbon-oxygen bond. And we want to resynthesize this drug with the nitrogen-nitrogen double bond. And we hope that by doing that, we'll have the ability to isomerize the drug from trans to cis back and forth without degrading it, just by irradiating it with light. Can you go next slide? And the reason we think this is going to be successful is because the drug's going to retain the same shape. If you go to the next slide. So one main concern we'd have is replacing a carbon-oxygen bond that can rotate freely with a nitrogen-nitrogen double bond. It's going to be relatively flat and a more rigid geometry. But we figure that we see here in our modeling that that's not really an issue. So figure A is our drug overlaid on top of BMS's. So BMS is in the red, ours is in the green. It's fitting right in at the same spot that BMS's drug fits in, and it still has some of the same hydrophobic interactions. Figures B and C are how our drug fits into the PD-L1 homodimer as a whole. So it's right in between the 2 individual subunits of the protein. And then if you zoom in, which is on the right, when the binding interfaces come together, it forms this little hydrophobic pocket. And that's what that little cutaway is that our drug fits in. So when our drug is in there, the hydrophobic interaction stabilize the binding of the 2 PD-L1 monomers. Go to the next slide. So the reason we want to make this drug as an azo molecule is we want to reduce the side effects surrounding it. So we hope that by having this azo bond, we can activate the drug in certain parts of the body using light only in areas where cancer cells are present, because immunotherapies have side effects all over your body. You know, you're administering these antibodies through the blood. It's a systemic therapy, and that's why your immune system will be attacking cells everywhere, and that's why you can get weird side effects from dementia to pancreatitis. It's almost like completely random. Go next. So San and Clara, they're both guilty of selling themselves short with, they're not giving themselves enough credit. And Dr. Shu was telling me this when we were going over this too. It's like, these syntheses are difficult because these are molecules that no one's made. It's the same thing that Clara and San did and everyone else in the group is doing. It's like, you can't just buy these chemicals off the shelves. We need to build them up. And if something fails, you got to go back to the beginning. So that's why that's the biggest challenge of having this 7-step synthesis here. But I'll go through steps individually. Next slide. Can you click through 3 more times? 1 more? Okay. So the first step is a Suzuki coupling. It forms a carbon-carbon bond between 2 aromatic rings. When we do this, it forms that the left hemisphere of the molecule. This is a good reaction that works every time for us, and we're able to do it safely. Next one. Yep. And so with that left hemisphere, we want to form it into a diazonium salt. So that's changing the aniline into a nitrogen-nitrogen triple bond. And if you go to the next slide, we want to do this for our Azole coupling reaction. So we can't do a Mills coupling because of that. The methyl group, which is ortho to the nitrogen-nitrogen double bond, is too sterically hindering. So we need to react diazonium salt with a resonance-donating phenyl nucleophile. And that, in this case, it'd be our 2,6-dimethoxyaniline. So this reaction works, and we have proof on the next slide. Come on, click through 3 times. So I don't really have the time to go through this whole NMR, but basically the NMR attributes the hydrogens to the hydrogens in the molecule. So we were able to prove that whatever sample we were analyzing here has the same number of hydrogens as the molecule that we attempted to make. So that's kind of how we know that we made it. I'll go to the next one. So the synthesis changed. Science really isn't linear. Things go wrong. You got to change, your direction. So we ended up having to change the two of the last steps of the original process, and I will highlight these on the next slide. So the first one is instead of making a bromine, we made it an iodine compound, and so it's going through the same diazonium salt reaction, and then we do a Sandmeyer reaction. That's what puts the iodine on the end. Go to the next slide. And we're actually able to make this one too. This was very important for us. And our proof is high-res mass spec from our colleague at Western Michigan, Dr. Mezzi. And so the middle peak right there at the 481, M plus Na, so that's mass plus sodium is equal to 481. So the molar mass of that molecule that we're trying to make is 458. And the mass of sodium is 23. So 481 minus 23 is 458, which is the mass of the molecule we're trying to make. So that's how we know that we've actually made this molecule, and we can do it again if we need to. Next. So then the final step, which is the new one, Samantha Dye and Claire Wagner actually pointed this one out for me, so shout out to them. This is a carbonylative amino homologation. Basically, it combines the original formulation and a reductive amination in a 1-step. And this is where we're at right now. It's taken a while because we want to do things safely here. It requires pressurized carbon monoxide as a reagent. So we had to get this special glassware here pictured below in order to run this reaction safely. But this is what's on the horizon right now. You want to go to the next slide? So yeah, that's about all I got to talk about today. So obviously I want to finish building this molecule, and then hopefully we can test its ability to change its shape with light. And then after that, we can test its ability to form those PDL1 homodimers or dissociate PD1 from PDL1. Next slide. So yeah, a huge shout out goes to Dr. Strew. He's been very patient with me over the past 4 years, and he's the one that gave me this project. Dave Carey, he's our lab tech, and he's giving us all our chemicals, making sure our machines work, and he's also making sure that we're safe in the lab, which is very important. The Albany College Chemistry Department, they taught me everything I know about chemistry, and I also want to give a shout out to Dr. Rollman and Dr. Rebecca. Those two were on my thesis committee, so thank you to those guys as well. First Cut and SRP, they've been financially supporting me to do all this work. And then my fellow lab mates, specifically Clara and Samantha, because they've helped me a lot with a lot of my synthesis. Next slide. Any questions?
And we already have one question,
Thank you,
which is, why can't you use NMR to characterize the molecule you did the HRMS for?
So we can use NMR. I originally had a picture of the NMRs in here, but I wanted to use the high-res mass spec because it looks, I mean, it's more definitive. But yeah, we can characterize this one with NMR. We actually have a good NMR of the sample that we took the mass spec of, so we have a good standard to go off of.
Okay, and I think we still have time. Another question, why the switch to iodine from bromine?
So we originally wanted to make we tried to do the Sandmeyer reaction with the bromine, but a lot of the reagents, it's like Cooper's bromide. It's like a lot of catalytic copper and bromine reagents that we couldn't get pure samples of, or we didn't have them around the lab. It just didn't work. And then we found iodine, it'd be a better leaving group, I'm pretty sure. And it was, it's a better reagent for the future reaction, which is the amino homologation.
And I think we're right about out of time.
Cool. Thanks, guys. Thank you for the wonderful compliments.
All right, thank you very much, Noah. Wonderful presentation. Before we move on to our next presentation, I just want to remind everyone that if you do have questions, you can put them in the chat, and Mike will ask them at the end of each person's presentation. Our next presenter will be Lexi Seidel, and Lexi's faculty sponsor is Dr. Vanessa McCaffrey. Lexi.
Hi. So if anyone has been here for a while, I'm going to throw you guys off a little bit. I'm not with Dr. Strew or working with drugs or cancer. So I've spent the last 2 years working with Dr. McCaffrey on the microwave-assisted Duff reaction. You can go to the next slide. So this is the general scheme for the Duff reaction. We start off with a phenol. We react it with HMTA and trifluoroacetic acid in heat. Thank you, Dr. Beeler. To form an imine intermediate, which is that the nitrogen double bond. And then after hydrolysis, we form a monoaldehyde or dialdehyde product, and the aldehyde is the oxygen double bond hydrogen functional group coming off to the left of to the right of the alcohol group. And that's something very specific to the Duff reaction. The major product is addition of the aldehyde to the ortho position or directly next to that alcohol. Some benefits of this reaction are that the reagents are relatively cheap and the reaction conditions are fairly mild. So I was able to do this in air. There was very little water sensitivity. So it was fairly simple to run through. Some of the downsides of this reaction and why it's not used as much industrially is that the reaction times take a long time. They can range from an hour, which isn't too bad, but can get to as much as a week just for that first step to happen. And the yields are also very mild, so between like 20% to 60%-ish which is not very high for industrial purposes. Let me go to the next slide. And so what this reaction forms are called aromatic aldehydes. They're very versatile compounds. They can be used as starting material for synthesis, whether that be medical, for drugs, pharmaceutical, or just standard chemistry research. They're also found in the cosmetic and food industries. They're fragrances and flavorings. You can go to the next slide. So the holy grail of organic chemistry is high yields and no side products. And as I just mentioned, the Duff reaction is not very high yield. high yielding, and there's also a little bit of issues with side products, which I'll get into a little bit later. And so we wanted to further optimize this reaction. And to optimize reactions, the goal is to increase efficiency, decrease reaction time, and increase yields. And so our goal was to optimize this reaction using a microwave reactor, and then to investigate the product distribution of the reaction. And the overall purpose of this reaction is just to make it more industrially useful. Like I said, it's a fairly straightforward reaction. It's just not efficient yet. So that was our goal, is to make it more efficient. You go to the next slide. So I'm saying microwave chemistry. I'm not using a kitchen microwave like most people would associate with the word. I'm using a microwave reactor, which is the image on the right. And if you go to the next slide, I'll talk a little bit more about the chemistry behind that. So conventional heating is heating basically from the outside in. So if you think of like a stove and a burner or a hot plate in the chemistry lab, you're heating whatever is holding your material or your liquid, so a pot or a beaker or something. And you have to heat the beaker or the pot, and then it would slowly work its way in, which leads to a really uneven distribution of temperature, as you can see in that little diagram on the right. What microwave chemistry, or what microwave heating does, is it uses microwave irradiation, which can go directly through glassware. It interacts directly with the molecules themselves, so we heat the molecules rather than heating the vessel, which then heats the contents. And this can lead to significantly shorter reaction times because it takes a lot less time to heat up, and can improve yield and have fewer impurities. And it's also a greener form of chemistry because it takes less time to heat something. So as I said, the Duff reaction could take up to a week to react just in that heating step. So you might be having a hot plate on for a week, which is just not efficient, as opposed to having a microwave on for just a few hours. We go to the next slide. So some of the we investigated 3 substituents. So that's that R group coming off of the benzene ring. We studied a methoxy substituent, a methyl substituent, and a nitro substituent. And we studied these substituents in each of the positions on the ring. So the top reaction is in the ortho position, where the substituent is directly next to the alcohol. The middle is the meta position, where it is 1 carbon away from the alcohol, and para is 2 carbons away from the alcohol. And what you can see from the first 2 reactions is that there's multiple products that can be formed. While I said the Duff reaction forms primarily in the ortho position, it is possible to get different additions depending on the substituent. And so that's one of the other downsides of this reaction that we were trying to limit. And so we studied the product distributions as well. If you go to the next slide. So these are our reaction summaries. We optimized the 3 positions for each of our 3 substituents. It's for a total of 9 reactions. We saw we got reaction lengths and temperatures of 95 degrees Celsius for about 5 minutes of irradiation, up to 95 degrees Celsius or 105 degrees Celsius for an irradiation time of 120 minutes. Comparatively, conventionally, these reactions for methyl and methoxy can take about an hour, and the nitro substituent can take multiple days. So being able to reduce that to 2 hours was pretty cool. The way that we optimized these reactions is I did about maybe 50 plus reactions, and just at different times, different temperatures, different conditions, and just saw what gave the best yields and the best product distribution. And so we also had some special conditions like hydrolysis changes, which ended up having better results than shorter hydrolysis times or a less concentrated hydrolysis. If we go to the next slide. So one thing that I mentioned earlier was the differences in monoaldehyde direction, like where it attaches to the benzene ring. And the nitrophenols gave a really good distribution of that, and it was very clear what our products were. We used NMR, which is related to the hydrogens in the molecule. So I was able to assign the peaks that we saw to hydrogens in the molecule, which is directly related to the abundance of this molecule in our final product. So the purple peaks are our major product, the intended product with the aldehyde in the ortho position, and the green in the ortho and meta, which is top and bottom, is the para addition or directly across from the alcohol. And we also have some starting material left over. But it was really nice to see this very clear distribution of our major and minor products, and that with the meta, there were 3 possible monoaldehyde additions, and we only saw 2, which was also very interesting to see. And then one other topic that I wanted to touch on was related to our methylphenols. So this is the optimal conditions of the chromatograms of our optimal conditions. But I really wanted to point out the peaks past 30 minutes that are labeled dimer. We saw these peaks. We didn't really know what they were. This was the first reaction that I had done my first summer. And this peak was not expected. When we looked at the mass spec, which shows the mass of this compound, the molecular ion, it was over double our starting material. So we really didn't know what it was or why it was forming. Dr. McCaffrey came to the conclusion that it had to have been a reaction of our starting materials with something else in the in solution. So we rolled with it. We noted it when we saw it. But then later in the summer, I was actually able to find a proposed structure. You can click on to the next slide, which is shown here. I found this or a related structure in the footnote of a paper, which is cited below. And when I replaced the substituents with the one that I was using, we got the exact mass of 269. The gas chromatogram is a zoomed in image where we saw those peaks. There are 2 peaks at 269. However, the mass spec was just shows the characterization kind of the molecule. That's in the weeds. There are different retention times, which means that they're slightly different. So what we believe is that it's just the way the molecule is arranged, so that rightmost phenol might be, instead of right next to that nitrogen-oxygen ring structure, it might be above, which might have resulted in the different retention time. But yeah, it was cool that we were able to figure that out. San actually proposed a mechanism, which we believe is very strong. I didn't include that, but it was very interesting to see. And if we had more time, we'd try to find a way to reduce it. Let me go to the next slide. So in conclusion, over the past 2 years, I've optimized 9 reactions using this microwave reactor. We have reduced reaction times of methoxy, methyl, and nitro. I missed that one, from hours to minutes. So like I said, the nitro group takes multiple days to react, and we were able to get it to react within 2 hours. So that was pretty cool. And then we also determined a complete product distribution for each reaction, which included the monoaldehyde and dialdehyde isomers, the dimer structure identification, and incomplete hydrolysis products, which is, if you remember back to the general scheme, that imine intermediate product with the nitrogen, just side reactions of that. And that's what I worked on last summer during FRSCA. And if you click one more time, some future directions. Dr. McCaffrey and I will be working this summer to prepare a manuscript for this research project, which would be pretty cool and hopefully get published. I will be taking a gap year next year to work as a collegiate development counselor for Delta Gamma, where I'll be traveling to chapters across the US and advising them and helping them further develop. And then in the fall of 2022, I will be attending the University of Oregon to pursue a PhD in chemistry. And next slide, sorry, acknowledgments. I would like to acknowledge Dr. McCaffrey and thank her so much for the opportunity and for all the help that she's given over the 2 years that we've worked together. A huge shout out to the Albion College Department of Chemistry and Biochemistry for everything, the instruments, the materials, and just that you guys are awesome. Dave Carey for making sure that we have everything and for keeping the chemistry department floating. And then FRSCA and Renee and everyone for the funding and time that allowed me to do this project. So I'd be happy to answer any questions if you have any now. Thanks, guys.
Lots of congratulations, but if anyone has any questions, please enter them in the chat. Especially really difficult questions. Okay, there's a question. So before you would publish, is there more lab work that has to be done?
I think there's always more work that can be done. As I was writing my thesis, I was still thinking of more things that we could test out, more things that we could try. So I think that would just be something we would add into like maybe future directions, but I don't think that the McCaffrey lab will be working on this project anymore. Thanks.
Okay, Dr. Lewis would like to know if there are disadvantages to using microwave techniques.
I can't think of any off the bat. It is possible that with the faster reaction times that maybe more complicated reactions happen just with the excitement. But other than that, I can't think of anything. I don't know if Dr. McCaffrey knows of any.
And we can squeeze in one more, I think. Dr. True wants to know, are there known uses for the unexpected product you found? We started looking at Novolac reactions. I don't know if there's necessarily uses for it, but I know that it's been studied. I don't recall any uses though. Okay, and one last question. What relationships between parameters did you notice? And in parentheses, time, temperature, solvent, etc.
Yeah. So something that was very clear is that reactions at 50 degrees Celsius just were not giving us the monoaldehyde product that we were looking for. So we stopped looking at 50 degrees Celsius. We looked at 95 degrees Celsius and up. The time and temperature, it depended on, or the time depended more so on the reactivity of the substituent that we were using. So the methyl and methoxy, there wasn't a huge, there wasn't a huge difference in distribution. And then the hydrolysis strength really helped with those methoxy distributions.
And I think we're probably out of time.
Yep. Great. Thank you very much, Lexi. Wonderful presentation.
Thanks, guys.
Let's move on to our next presentation. Our next presentation will be given by Venkata Chintapalapati. Sai's research sponsor is Dr. Dave Ryman. Sai?
Yeah, thank you for the introduction, Dr. Beeler, and I'm happy to get into this. Thank you all for being here today. The title of my honors thesis in computer science, which is definitely a break from all the fantastic chemistry presentations, is Decentralizing the Web, Hosting and Accessing Websites on the Blockchain. And like Dr. Beeler said, my faculty sponsor and primary thesis advisor is Dr. Ryman. So thanks a lot to him. Could you go to the next slide, please? So first of all, before I go into exactly what I did, I thought it was important to go over a few key concepts, such as the World Wide Web. I'm sure we all know what the World Wide Web is, and use it on a daily basis to share and access information, whether that be through like Wikipedia or even Netflix. So this was actually invented by this gentleman named Sir Tim Berners-Lee, and he intended for it to be a universal medium for sharing information. So this was actually a technology that was built on top of the internet. So the internet had already existed and connected together actually millions of computers beforehand. And the difference is the internet was essentially all the technologies and protocols such as email and ones that had to do with file transfer. And the World Wide Web really brought an interlinked web of documents in which there's hypertext documents which could be styled, all that, and even have links within the text in order to link to other web pages or websites. Each website, there's websites that consist of one or more web pages. So that's essentially an overview of what the World Wide Web is. Could we go to the next slide, please? This is essentially a quick diagram of how it exactly works and all the protocols that go into it. So if you want to access a website or a web page, you type it into your client. You type in the URI or the identifier of the website, such as like google.com, and that using that, the web browser actually fetches the web page from the web server. using these protocols that Tim Berners-Lee actually created, such as HTTP and HTML. So it fetches it using HTML, and the server returns using HTTP. The server returns an HTML document that contains the data of the website and essentially the styling of it, how it's supposed to look, and the HTML code actually defines the layout of this web page. So based on this, as you can see, I mean, it's feasible for the web server to go down. That could be either like a government censorship, or it could just go down because no one was paying the hosting bill, or it could also be hacked. So those are some downfalls of the current client server model of the World Wide Web. And I had an idea to change that model using blockchain technology. So could we go to the next slide, please? Yeah, so essentially on a web server, the most primitive form of a website is essentially website code stored on a web server. So this is just a quick example of just a code of a very simple website that I created. So this is what I want to host on the blockchain. It's just, after all, it's just data that we can store anywhere else. And I thought it'd be cool to store it on the blockchain, which brings us multiple advantages. All right, could we go to the next slide, please? Yeah, so blockchain technology, I'm sure you've heard of it in the context of Bitcoin, since it's actually the foundation of Bitcoin, and Bitcoin is an electronic currency that allows two parties to exchange money, basically, without the supervision of a central entity, and without a central entity having power over the transaction. So blockchain, the technology of blockchain, is actually a decentralized ledger, which essentially stores data, and it's a chain of blocks and characteristics that come with this model. I'm not going to go into the nitty-gritty technical details, since there's a lot to go into. It's a whole big rabbit hole. But the characteristics of this technology is that any data put onto the blockchain is immutable, meaning that cannot be changed or deleted at all. So once it's there, it's permanent forever, for the life of the blockchain. And it's also decentralized. So there's nodes in a blockchain network, which are simply devices that take part in the network, and those store data on the blockchain. There's thousands of them. So essentially, there's thousands of copies of the blockchain going, all around the world. So it's very hard to take it down as a result of this decentralized characteristic, since you essentially have to take down much of the internet. And also, due to every node on the blockchain network storing data that's on the blockchain, it's very transparent. Anyone can see the data, anyone can access the data, anyone can see who published the data, things like that. So because of these characteristics, it's been popular most recently with many uses, such as banking, funds transfer, contracts, and also storing things like electronic health records. So since we can store arbitrary data like that on the blockchain, I was thinking, can we store website code? Could we go to the next slide, please? Yeah, so essentially what I did in my thesis project was I stored and accessed websites on the blockchain by creating some computer programs in the Python programming language. So first of all, I created a website blockchain web publisher, which takes in website code and converts it into a string of hexadecimal characters, and adds it into an Ethereum transaction. So Ethereum is simply a type of blockchain, and it adds it into a transaction on the Ethereum network, which can then later be accessed using this web browser that I created, which fetches websites from the blockchain based on their transaction ID. And all of this actually costs some money, because it costs money to put things on the blockchain, because you need to incentivize those nodes to store the data, essentially. So what I did, it didn't cost much, but there's definitely a limitation of cost with this method. Could you go to the next slide, please? Yeah, so here I have a demo of the computer programs I created. Of course, if you want to see the actual code and what goes into this, I'd be happy if you checked out my thesis. So Dr. Wheeler, could we play that video? Dr. Wheeler? Did we lose him?
He does seem to be frozen. I'm going to try to contact him.
Okay, thank you. Yeah, if this doesn't work, I can just put a link of the video in the chat and you guys can have a look.
Yeah, I think you're going to need to. Dr. Beeler tried to play the video and his computer crashed. So.
Oh, really? Okay,
you
okay.
might need to skip ahead as best you can.
Okay, sure. I'm just going to put the video real quick in the chat. 1 second, please. Would it be possible for me to share my screen?
Yes, sure.
Okay. It's actually grayed out. Would you be able to change that, or should I go?
Hold on just a sec.
Thank you.
Okay, now give that a try.
Sure. Okay. Sure. Okay. Actually, yeah, there's no audio on this, so I think hopefully. Can you guys see this?
Yes.
Okay. Okay. Cool. So here's the quick demo of my blockchain web browser and publisher. So these are just some website files that we want to put onto the blockchain. The HTML documents, including websites as well, and styling. So what we need to do at this point is compress it into a compressed zip file, which puts all the website files into one. And then from here, we can access my computer program that I created and pass it the website zip file. And what we can do from there is once we simply run it, it publishes it onto the Ethereum blockchain and gives us a transaction ID. So once it goes through that, we can simply copy the transaction ID it gives, and that's the website. That's the location of the website, and that's going to be accessible for as long as the Ethereum transaction exists, which is for the foreseeable future. So we can go to this website, this blockchain web browser, which I also created in the Python programming language. And if you simply paste that transaction ID and click enter, you get access to the website. So anyone can access this, and it's very hard to block as well. So anyone can access this, and you can click through to other pages of the website, use any functions of a web browser. Okay. So I guess the impact of this project is that it's very resistant to deletion or modification due to the decentralized and immutable characteristics of the blockchain. And this website cannot be deleted ever or modified. And due to the blockchain characteristics as well, it's always available. It's always available to anyone, and it's very hard to be blocked, and it never goes down, essentially. So these characteristics bring an interesting use case for this technology, as it can be used for archival and that of websites. So in the case of say Facebook or something, if it goes down, you can always access it via an archived version that can be archived on the blockchain. So there's definitely some limitations to this technology and some further research that needs to be done. One of the important things is that websites that have dynamic web pages cannot be stored, such as if any website that needs a login, since at that point the web server has to dynamically generate the website, and it's different for every single client. So for that reason, those are not able to be stored on the blockchain. And another limitation is money. So the very simple website that I stored costed about $8. And that was very, very simple. It was on the order of kilobytes, the size. And many websites can go up into the, the average website size is around 2 megabytes. So that would cost a lot of money. And further research that could be done with this is creating a kind of a new blockchain network specifically made for website storage, and there's research being done on things like, there's this one named Permacoin. So those technologies could really bring down the cost of this and make it available to the masses. And I think, I hope this proof of concept is a step towards that. So this couldn't be done without my fantastic thesis committee members, Dr. Ryman, Dr. Voss, and Dr. Mason. So thanks a lot to them. And if you guys want to read my thesis, that'd be great. If you want to see the really technical nitty-gritty detail of how the blockchain works and exactly the code behind these computer programs that I created. If you have any questions, I'd be happy to answer them.
Okay, and we have one question already. And by the way, well done, given the technical difficulties.
Thank you.
The question is, could this technology be used in states that control the free press?
Yeah, it could actually. So it's something that's definitely, that's one of the use cases for, let's say, like whistleblowers. If they want to publish something, if they publish it on the blockchain, it can never be taken down. And since there's many nodes, and it's unfeasible to block all of them. So that's definitely one of the main use cases for this technology, in that to avoid government censorship.
I think we're right about at time, and Dr. Beeler is back.
Okay.
Yes.
Thank you very much.
I'm very sorry, Cy. My browser crashed when the video started to play. Maybe your blockchain browser would take care of that problem. So I'm going to go back to share my presentation.
Thank you all.
Thank you very much, Cy. Wonderful presentation, even with the glitches that I imposed on you. So we can move on to our next presentation, which will be given by Claire Mitchell, and Claire's faculty sponsor is Dr. Mark Bowman. Claire.
Hi, thank you for the introduction. So I'm Claire, and today I'm going to be talking about casino. I actually heard Dr. Bowman give a talk at a colloquium I was at my sophomore year about the idea of turning euchre into a casino game. And I was really interested in, so I ended up doing 2 first goes with him and writing my senior thesis on this topic. So when I jumped onto the project, he already had an idea of the adapted rules and what he thought might work for a casino game. If you wouldn't mind clicking the next slide, please. So these are some of the differences between the original version of euchre and our adapted version that we started with. So original euchre, there are partners of players, and they all get 5 cards, and they determine the trump, and then they play against each other to win tricks and win inevitable points. And there's different point systems for different number of tricks won and different factors. And in our adapted version, the player gets 3 cards, and the players are not playing against each other. They are just playing individually against the dealer, sort of in a blackjack type situation. And the trump is just dictated by the flip of the top of the deck and not by any player or dealer choice. If you wouldn't mind the next slide, please. So I started off with some research. Dr. Bowman gave me 3 books that he thought would be good. If you wouldn't mind switching, thank you. So the first book I read was The Essentials of Casino Game Design. This book was, I think, probably my favorite one. It talked super in depth about the conception of games, what makes a great casino game, ideas like names, logos, things that were important, and different adaptations. The following book was sort of an intermediary between conception and math. And so it talked about some of the more basic math that goes into casino games, like house advantage and how that applies. And then Basic Gambling Mathematics by Dr. Bowman is just all of the math that you could ever want behind a casino game. So that was super helpful in the math phase. Next slide, please. So first was gameplay. I had to get a feel for the rules that we had set in place. And so I played about 300 hands with anyone who was willing to play. And so I'm going to do a simulation of how that kind of worked so you can get an idea of how this game works. Next slide, please. So the first important thing about Euchre is the ranking system. So each card has a rank and some cards are higher or lower. So the rank is based on the trump suit, which in this case of this picture is the hearts. So the highest card is your Jack of Hearts, which is your right bower. The next highest card would be your left bower, which is the Jack of the same color but opposite suit. And then it follows Ace to 9 of all of the trump suit, and then Ace to 9 of all of the non-trump suit. An important rule in Euchre is you must follow suit if possible. Next slide, please. So this is a setup of the game. The player gets 3 cards, the dealer gets 3 cards, you place an ante into play, and then the trump is declared. So in this case, the trump is a club, and I have the Jack of Spades, which is the left bower. So that is a very good card. And then I also have an ace, which is high, which is a good card, and a 9 of spades, which is a trash card. And next slide, please. So I decide to play, and so I place in 2 more chips, and thus having 1 for each card against the dealer. Next slide, please. And so then the dealer flips their first card, and their card is the Jack of Hearts. And I don't have any hearts to play, so I don't have to follow suit, and the only card I have that would beat this is my trump, so I want to play that early and secure my win. Next slide, please. So I play that, and then next slide. Thank you. I won that trick because I beat it with my trump, so I got a chip for winning. Next slide, please. The dealer's next card is then the 10 of clubs. I don't have anything that I can use to beat that, so I'm going to throw away my worst card, which is the 9 of spades. Next slide, please. And so I throw that away, and then next slide. And then I lost that one, so I lose a chip. And then the following slide, please. And then the dealer's final card is the King of Diamonds. Next slide, please. I play my Ace of the Diamonds, and next slide. I win that one, and so I won a total of 1 chip net worth because I placed in 3 initially and got out 4. So that was a good hand for me. I won and beat the dealer. Next slide, please. So after doing that many times, especially with Dr. Bowman, we played for like 2 hours, and I was playing as the player, he was playing as the dealer, and I felt so discouraged the entire time. I was losing like nobody's business. I did not want to play anymore, and if I didn't want to play and I was supposed to be researching this, there was no way a casino player was going to want to play this. And so we decided that the house advantage was too much in the dealer's court and not enough in the player's court. So I did some research, and I remembered something I read in the casino game design about a common adaptation to already existing casino games was to add an extra card into the player's hand. And so I thought if the player started out with 4 cards and they got to discard 1 in the beginning, they would have a better chance at a better hand because they could get rid of their lowest and have more cards to choose from. And it would also give the player a sense of control and agency in the game, because previously you saw they follow suit with the dealer. They just they're completely dictated by the dealer and don't get much personal choice. And so this gives them a little bit more like skin in the game, a little bit more confidence, and a little bit more commitment to the game. And so I played hundreds of more hands at those rules with everyone and asked everyone I played with if they preferred playing with the 3 cards or the 4, and everyone preferred the 4 cards. And so that became a permanent rule change. Next slide, please. So these are the final rules. You can read them, but it's the same as the simulation that I played, except you get 4 cards and you get to discard 1. Next slide, please. So next was the math. The initial plan to come up with a player the game was to just calculate the probability of winning certain hands against the dealer's hands. This proved difficult. It worked well for the more dramatic hands, like the really like, oh, you have the Jack of Hearts, like the trump card, you have the right bower, like obviously you should play, or like you have all 9s of non-trumps, like you should. Obvious hands were easier, but we were calculating more intermediary hands, and some examples are as follows. Next slide, please. So probability is the base of all math casino games. It's the probability you're going to lose all your money or the probability that you're going to hit jackpot. So one of the most common probability principles used in casino mathematics is combinations. So it's the idea for finding a number of ways that you can choose something from a larger set. So in this case, it'd be the number of ways you can choose cards from a deck. And so the formula can be seen below. I'm not going to really go through it. But so an example of how it can be used, though, is how many possible ways can the dealer's hand be dealt from the deck? So the deck is 24 cards, and the dealer gets 3 of those. So it's 24 choosing 3 cards, which is 2,024 ways. Next slide, please. An example of how this math was used to actually determine the probability of good hands versus bad hands is in this case, which is what is the probability the dealer has at least 1 trump if you have 1? So the probability the dealer has at least 1 trump is the probability that they have 0 is subtracted from 1, the total ways. And so there are 7 trumps in a deck, and you, the player, have 1, and there's 1 on the top of the deck to tell you what the trump is. And then there's 17 non-trump cards, and you have 2 of those, so there are 15 available. And so the probability that the dealer has none of those is first 5 of the 5 trumps, they have 0 of them, so 5 choose 0. And then of the 15 non-trumps, they have 3 of them. And then that's out of the total ways that they could have any of the cards, which is 20 choose 3. Next slide, please. And this ends up being 60%. This is the probability the dealer has at least 1 trump, given that you have 1 in your hand. So this would make the dealer think about their choice. If they had a very low trump, they might not want to play because it is likely that the dealer will also have a trump and thus could be higher. So these probabilities were very difficult to calculate for the middle hands. I didn't have enough time. I couldn't account for all of the variables, and it was just a pain. So we decided a code was the next way to go. If you could go to the next slide, please. So we ended up creating a computer program. I had very limited computer programming skills before this. I had taken Computer Science 1, knew basic Java, and that's what I was going off of. So we started this code very early on in the presentation, or in the research, and I started creating deck classes, code classes, and then compiling the game. Next slide, please. Overall, I wrote 1,000 lines of code, and it gives this output as a sample output. So you get your cards, your trump is declared, you're told your chips, and then in this line, play this hand, you have 2 or more trumps. That's where the player strategy comes in. And that's what was updated continuously as I came up with new strategy. I updated that so that it would give more and more accurate advice. And then it asks you if you want to fold, you remove your card, and then you play against the dealer. And here it says you have to play King of Hearts 1 after in your first hand. That's because the dealer's card was a heart and you have a heart. And so since you have to follow suit, it's telling you that's the card you have to play. So I played that card and I lost because I couldn't beat the card. And then I ended up winning 2 and losing 1. You can see that on the right-hand side, and it tells me my total chip count, and I could continue that if I so choose. And so this didn't give me the quite cut and dry player strategy that I wanted. I had played this many times and recorded of the high cards, low cards, and medium cards, what was good. And I'd come to the conclusion that having a trump card and any high card, which is a king or an ace, was a good hand and you should play. But I wasn't satisfied with the amount of data I had produced, so I decided to create another computer program that tested players' hands. So I could assign the player certain hands and then test the rest of the deck against that hand as possible dealer hands and decide which was good and which was bad. And so I found a cutoff at 2 non-trump aces. Anything below that was not a successful hand, but anything above that was. So the strategy ended up being a trump and a high card, or 2 aces of non-trump, or anything higher than those 2 things were successful. Next slide, please. So finally, as a cap off to my project, I did some art. I personally am a huge fan of art, so this was just a fun way for me to incorporate that into my project. Next slide, please. So I started with a logo. Every good product needs a logo, and so I created this one. I used colors that symbolize wealth and luck, opportunity, fortune, and these colors are also common in a lot of casino games for that reason. And then I wanted to display a common euchre theme, which is the bowers. So I included all of the jacks as possible bowers. And then next slide, please. And then I used this logo to create a rack card. This rack card would be displayed in casinos as the rules and give them an idea of what they're playing before they step up to the game. Next card, please. And then finally, the felt design. I designed the table using the logo and other aspects, and it has the ranking system on that for the players to reference while playing. It has spots for all of their cards and their antes. Next slide, please. Finally, last but not least, a thank you to Dr. Mark Bowman for being my advisor and giving me this idea and his support along the way. To Renee Krieger and Dr. Vanessa McCaffrey for their FERSCA support. My brother, Grant, he's a computer scientist, and he helped me immensely with my code. To Nico Van Eck, as pictured on the right, he was essential for debugging my code. He was my rubber duck debugger, if you will. And I would like to thank the victims of my relentless pursuit of players for Casino Euchre, because I was persistent. I'd also like to thank all of my committee members and, of course, my mother for all of her undying support. Thank you.
Thank you, Claire. And we've got a couple of minutes for questions. And so far we've got the question, what's in the cards for you?
I'm gonna assume that means after graduation.
I think so.
So I'm actually going to be working as an actuarial analyst at Auto Owners Insurance in Lansing when I graduate.
Great. Congratulations.
Thank you.
One more question, and I think we still have a minute to go. What are the prospects of this game entering the casino industry?
So it's actually very expensive to get a casino game into the actual casino. It's around $100,000. You have to pay for patent lawyers. You have to pay for all of these things. So unlikely at this point, unless anyone's willing to donate $100,000, I will be accepting. But we also think it may be a great version of like an online app sort of gambling situation, or maybe a computer interface in a casino, because one of the problems we had that we couldn't quite figure out how to solve was the forcing of players to follow suit. Unless there's like a bouncer behind you checking, it's kind of up to the player to be honest about following suit. But if it was on a virtual platform, the program could force them to follow suit, which might solve that problem a little bit better. But unlikely that it's actually going to be in a casino game at this point.
Okay, great. And I think that brings us to the end of our time. Thank you.
Great. Thank you very much, Claire. That was a wonderful presentation. Okay, we can move on to our next presentation. There, we get the slide deck going. Anna Chrysler is going to be presenting next, and Anna's faculty sponsor is Dr. Craig Strew. Anna?
Hello, everyone. Thank you for that introduction, Dr. Beeler. Like you said, my name's Anna. I'm a junior biochemistry major, and today I'm presenting my project entitled Generating Antimicrobial Nanobodies Through Directed Evolution. Next slide, please. So antimicrobial resistance is one of the worst threats to public health across the globe. Bacteria and other microbes can evolve mechanisms that deactivate antibiotics that are supposed to kill them. And so this figure here outlines the projected deaths by this issue by 2050 if no urgent action is taken. And so this is about 14 times higher than the numbers we see today. So this is a very urgent problem. Bacteria evolve these mechanisms very quickly, and so we need a rapid solution. And so this is very important also because without antibiotics, simple infections like a scratch on your hand where you just go to the doctor to take an antibiotic would no longer be able to have a solution. And so the pharmaceutical industry is also at play in why we don't have a good outlook on antimicrobial resistance. There's not a lot of investment. And so all these things together pose a really big problem that we need a solution to. Next slide, please. So my project is modeled mechanistically off of vancomycin, which is a glycopeptide antibiotic. This targets the peptidoglycan of gram-positive bacteria. And so the reason these antibiotics are so effective is because peptidoglycan surrounds cells. It's their cell wall. And so if you can destroy their cell wall, you kill the cell. And so that's what makes them an effective antibiotic. And so I have outlined here the way in which this works. And so glycopeptides like vancomycin bind and cap the dealanine motif of lipid 2 in peptidoglycan synthesis. And so it blocks both transglycosylation and transpeptidation, which are just two processes that make peptidoglycan. So if that doesn't happen, then the cell doesn't have their cell wall and they die. So for my project, we want to build a model for creating effective antibiotics against resistant pathogens and keep up with the rapid speed of antimicrobial resistance. Next slide. And so the reason we're using vancomycin as a model is because it's a really effective antibiotic. It treats a variety of infections, some of which I've included here. C. difficile impacts about 500,000 Americans each year, causes a lot of hospitalizations, and vancomycin will also treat staph infections and other antibiotic-resistant infections. But unfortunately, the problem we're facing is that vancomycin, this last resort antibiotic, is also facing high levels of resistance. And so we are in a tough spot where we need to find more effective antibiotics and more antibiotics that work against these resistant strands. Next slide. So for my project, we're looking at a type of antibody as a potential drug. So I'm sure we've all heard about antibodies with COVID and how they've been a powerful biological tool being used to treat some of these infections. And so we're looking to do the same thing. I've shown here in this picture the structure of a typical antibody found in the human immune system. This is an IgG antibody, and it has 3 distinct regions. There's an FC region, which is a conserved region recognized by the human immune system. And then there's 2 Fab arms, which are consisting of a light chain and a heavy chain. And importantly, within these Fab regions are variable domains. And so each variable domain has 3 complementary determining regions. And so that can kind of be seen in this right figure with this ribbon diagram. And what's so important about these is they give antibodies hypervariability. And so each loop is consisting of 12 to 14 amino acids. So if there's 20 common amino acids, they can be in any order in that 12 to 14 loop. And there's 3 loops. So that's almost an unlimited amount of combinations, which leads to almost an unlimited amount of potential targets that these can bind. So they're a really powerful tool that creates massive diversity. And the technology that I use for my project relies heavily on this diversity. Next slide, please. So antibodies can be engineered into different fragments, and specifically for my project, we're looking at the VHH fragment, which is just a single variable domain of the previous slide. You saw I showed a variable domain. That's what a nanobody is. And so it has a small fixed sequence with those 3 complementary determining regions. And these are nice for potential drugs because they have a lot of drug-like properties, some of which mean they're very small, they're stable, and they have the potential for high specificity. Next slide. So directed evolution harnesses the power of evolution, but does so rapidly. So this is kind of the perfect solution to antimicrobial resistance because it's a method that works quickly and can combat the fast speed of antimicrobial resistance. And so the method that we use is yeast surface display. And on the left here, you can see kind of a zoomed up picture of what a yeast surface would look like with nanobodies. So these yeast cells have DNA that allow them to express nanobodies on the surface of their cell. And so in this naive library, moving to the figure on the right, there's billions of different yeast cells with slightly different DNA that allows them to have slightly different nanobodies. So there's billions of different nanobodies in this library, and then you can bind them to whatever antigen you like to remove what doesn't bind to that antigen and keep what does bind. And so you can enrich this over and over again and just have the best, highest affinity binders to whatever you're looking for. Next slide, please. So for my project, our antigen, like I said, models vancomycin. And so we use the peptide in peptidoglycan as our antigen target. And so we want to find nanobodies that work like vancomycin to bind and cap dealanine. And so that's what you can see here. We've labeled our antigen with biotin because the way that you select what binds from what doesn't bind is through cell sorting techniques. And that's where you see a streptavidin labeled bead. This is magnetic. I'll get to that in a moment. But the important part of this is the streptavidin binds biotin very tightly. And so you can separate your yeast cells that bind to your antigen because they bind the biotin and the streptavidin, and then you can just remove that whole complex from what doesn't bind and get your binding cells, which will be potential drugs. Next slide, please. So I mentioned the magnetic beads. That's because we use magnetic activated cell sorting. And so you have a naive library of cells that you can incubate with your antigen as well as those magnetic beads and allow them to bind. So what's going to bind will stick all together and what doesn't won't. And you put these through a column that's attached to a magnet. And so what flows through with the presence of the magnet is what's not attached to the magnetic bead. So you remove those from the column and you remove the column itself from the magnet with a new tube, and you can collect what did bind. So by removing the magnet, you're able to collect the cells that were originally bound to the magnet. And you can do this with a variety of different conditions. So you can do a negative selection against just the beads themselves to get rid of off-target binding, which we've done. But whatever the conditions may be, you're left with optimal binders to your antigen that you can send off for analysis. Next slide, please. So the instrument that we used is a flow cytometer, and this works basically by having a beam of light that detects fluorescence, and that sends that to a computer and produces data that we can interpret. And so in this upper right-hand figure, you can see there's a green star and a red star. So the basis of this instrument detecting the fluorescence is that we have two different fluorophores. And so the green fluorophore you can see is binding that C-MYC tag. And so when the instrument detects this green fluorophore in this case, that is showing that we have nanobodies on the surface of our cells, which is important. If we want to select nanobodies against our target, we first need cells that have nanobodies. So that's good to know and good to have data for. And then the red fluorophore, if the instrument detects that, that means that yes, we have nanobodies, but we also have nanobodies that are binding to our target. So this is a great way to distinguish what types of cells we have. So do we have yeast cells that are in fact producing nanobodies on their surface? And do we have yeast cells that have nanobodies that are binding to our antigen? So you can go on to the next slide. And so these are results from flow cytometry data done at the University of Michigan. We're very grateful that they were able to run flow for us. And so there's a lot going on here, so let me walk you through it. If you look at either figure A on the x-axis, that's kind of what I was saying with that green fluorophore. So the x-axis is looking at display. Do we have nanobodies? And the y-axis is looking at antigen binding. So if there were yeast cells that were displaying nanobodies and binding to our target, we would see dots in the upper right-hand quadrant because each dot represents a yeast cell. And so overall, our results do show that we don't have any significant antigen binding. You can see with the control versus the highest antigen concentration, so A and B versus C and D, there's not a big difference there. And we would expect to see in the highest antigen concentration a significant population of cells in that upper right-hand quadrant, which we don't see. However, it was very helpful to be able to have two different libraries to do directed evolution against. And so we can see that the Tessier lab, which was given to us by the University of Michigan, or the Tessier library, excuse me, does have better display. And you can see that on the right hand of the graph. So there's like more dots, a higher density of dots on the right side. So we do see more display. And that Cruise library was commercially purchased. And so we will likely, moving forward, only use nanobodies from the Tessier lab. Next slide, please. So moving forward, we would like to select binding nanobodies, and I've actually included some fluorescence activated cell sorting FACS data here, just to show again, we want to see cells in that upper right-hand quadrant. And so briefly, FACS is just like flow cytometry, except that instead of just outputting what types of different cells we have, it will actually sort them for us. So moving forward, if we do have binders, that would be very nice to be able to collect our binders from other cells. But I just wanted to show this because we will want to see dots in the upper right-hand quadrant. And then in order to actually get binders, we're thinking that switching to an antigen that's the entire lipid 2 instead of just the peptide antigen might work better to offer more binding, like a bigger binding surface, just because the antigen is very small compared to the nanobody. And we also might try an SCFV library. In figure 1, you can see that an SCFV is a little bit bigger than a nanobody. This is because it actually has 2 variable domains instead of just that 1 variable domain. So we're thinking if we can have 2 variable domains to bind, we might get better binding to our antigen. And then this summer, I'm actually going to be working on the mutated antigen in vancomycin-resistant bacteria. And so the basis of this is it'd be nice to have a nanobody that works like vancomycin, but like I said, vancomycin is facing high levels of resistance. And so we want to find a nanobody that works against the resistant bacteria. And that can be seen in figure 2. So like I mentioned, I had a peptide that had dealanine at the end. The resistant bacteria has a peptide that's dealanine D-lac or serine. And so this summer, we're going to try to select nanobodies against this peptide and potentially create a nanobody that's effective against vancomycin-resistant enterococci. Next slide. I'd like to acknowledge all the people listed here over the years for all of their help, and just especially throughout this crazy past year, creating a safe lab environment and able to have fun and get stuff done. Next slide. Thank you all for listening, and I will take any questions that you have.
And a reminder, please send your questions through the chat feature. First question, how efficient is the magnetic separation process?
It can actually be done in a matter of hours. I don't know if efficient meant time, but when we've done it in lab, it can vary from a 2-hour process to like a 5-hour process, but usually it's between a couple hours.
Lots of congratulations coming in. Any more questions? A follow-up question, how about efficient in terms of separation?
Yeah, so I feel like that could be answered in several ways. So the flow through is collected, what doesn't bind. So that actually just flows through the column, and then we will plunge or elute out the binders. And so I would say it's pretty effective in separating binders from non-binders, but in that process, if the binding affinity isn't super strong, then potentially the antibodies could be removed from the magnetic bead. But if we did have binding antibodies to show for it, we would actually know this efficiency, but unfortunately we don't really have any binders, so it's hard to say.
One last question, where do you get the targets?
So we commercially purchased the peptide pre-labeled with the biotin, and so we got it from a commercial source.
Okay, I think we're about out of time.
All right.
You, Anna.
Yes,
thank you so much.
Thank you very much, Anna. Wonderful presentation. Great talk. We will now move on to our next presentation. Hannah Woods will be presenting. Hannah's research advisors were Dr. Vanessa McCaffrey and Dr. Nicole Zellner. Hannah.
Okay, hi everybody. Thank you for the introduction. So like you said, my name is Hannah Woods, and I'm going to be talking about the assessment of amino acids observed in carbonaceous chondritic meteorites and how they have implications for survivability and impact events. And so I have been working with Dr. Vanessa McCaffrey and Dr. Nicole Zellner for a few months now on this project. And so next slide, please. And so when I was first introduced to this project, I thought of space as a very vast open area, but however, there are many complex molecules in space, such as sugars, ammonium, and lots of water. And these things are found in extraterrestrial objects up in space. And so among these complex molecules are amino acids, which are simple organic compounds containing both a carboxyl and an amino group. And so a picture of an amino acid can be found here on this slide. And it is in its generalized and neutral form. And so these amino acids have been brought to Earth by meteorites. And so these objects have been ejected from planetary objects in space. They have survived Earth's atmosphere and have impacted our surface. And so a picture of a meteorite can be found on this slide as well. And this meteorite is called Murchison. And it is one of the most well-studied meteorites that has been analyzed for amino acids. So next slide. And so Murchison is classified as a carbonaceous chondrite. And so this is a stony meteorite that contains high levels of water, carbon, and organic material. And so carbonaceous chondrites are put into different subclasses based on their primary and secondary characteristics. And so on the right of this slide, as you can see in this chart, the very left of this chart shows the chemical type of these subclasses, the chemical characteristics in different classifications. So that's what all those letters are for. And at the very top and the bottom of these charts show the aqueous alteration and thermal metamorphism and the different degrees of this. And this is the secondary classification of these meteorites. And so what aqueous alteration means is that is the transformation of molecules into organic material in a hydrated environment. And then thermal metamorphism occurs when the alteration temperatures are too hot to retain a hydrated environment. And so aqueous alteration typically occurs around 0 to 300 degrees Celsius. And so above this is when meteorites will experience more thermal alteration. And so more aqueously altered chondrites are given a value classification of either 1 or 2, and the more thermally altered are 5 or 6. And so amino acids have been known to appear in these carbonaceous chondrites in many different subclasses. And so this project assesses amino acid concentrations of these various carbonaceous chondrites. So next slide. And so there's been a lot of controversy about whether or not amino acids are even able to survive impact when they hit the earth. And so amino acid survivability has been investigated experimentally where meteoritic impacts are mimicked. And so we are going to compare the concentration results of natural amino acids to the amino acid survivability concentration of amino acids after impact. And so hopefully with the understanding of this amino acid survivability, this could lead us to eventually identifying the formation mechanism for which these amino acids are formed and found in meteorites. So next slide. Thank you. And so to start this whole collection process, I basically just pulled a bunch of amino acid data, concentration data from various sources that assess natural meteorites. And so a variety of these sources assessed amino acids in carbonaceous chondrites, and some of them assess amino acids in non-carbonaceous chondrites. And so on this slide are just a few examples of the data that was presented in these papers and how they were exactly presented. So next slide. Thank you. So each amino acid side chain was classified according to 3 different criteria: branched versus linear, heteroatom versus CH side chain, and cyclic versus non-cyclic. And so if you look at the top corner, the top picture on the right, that is an example of cysteine, which is a heteroatom side chain because it has an atom in its side chain other than carbon and hydrogen. And then on the one next to it on the left, that is valine, and it is a branched side chain because its alpha carbon is attached to 3 or more carbons. And on the very bottom is proline, which is a cyclic amino acid because its side chain, the atoms form a cyclic ring. And so these are common amino acid structures, and they gave me an opportunity to look at the data in 3 different ways. And so I calculated concentration percentages, which are focused on the different concentration of amino acids within each meteorite sample. And then I calculated number percentages, which focus on how many different amino acid structures are in the overall data set. And then next slide 2, please. Thank you. And so then I also pulled various amino acid data from sources that focused on impact experiments. And so on this slide, I just kind of include a little example of what a typical impact experiment would look like. And this is from a paper by Peterson. And so briefly, a gun with its barrel extending into a vacuum chamber is just used to launch a projectile to a desired velocity into like a given target. And so for this impact data that I collected, I actually calculated the survivability percentage instead of concentration percentage for these amino acids. Next slide. Thank you. Okay. And so these are my results of the concentration and number percentages for the natural amino acids in these carbonaceous chondrites. And so I'm not showing you the full data set right now. This is the final compiled data and the final analysis, just in the interest of time. But we can still get a really great idea about how the composition of these amino acids are distributed throughout these carbonaceous chondrites. And so if you look at the graph on the left, this is the concentration percent average of amino acids. And so the linear percent average and the CH side chain percent average are presented here on these graphs. And I actually organized these carbonaceous chondrites in order from decreasing to increasing temperature range. So if you look at yellow and red, this is CV and CK chondrites, and they experience the highest temperatures out of these carbonaceous chondrites that I analyzed. And so these chondrites, they experience the highest temperature and they have the highest linear side chain percentage averages. And so this is what we expected to see, because at lower temperatures, we expected to see a high composition of amino acids with branched side chains due to increased stability of branched side chain versus linear. And so this is true. So at higher percentages, we see lower percentage of branched side chains. These chondrites, the CV and the CK, they lack aqueous alteration, which means that they have no water within their system. And so they also have a higher frequency of heteroatom amino acids. And this is actually the quite opposite of what we kind of expected. We expected that carbonaceous chondrites that experience more aqueous alteration would have higher amounts of heteroatom amino acids, or sorry, yes, they would have higher amounts of heteroatom amino acids because any liquid water within that system, within the system of the meteorite, would react and possibly be incorporated into the structure. And so CV and CK, they lack aqueous alteration, yet they show the highest heteroatom side chain percentages. And so this suggests that maybe the side chain alteration may not be the dominant mechanism in the synthesis of these amino acids. So then if we look to the right of this graph, this is my number percent averages. And so this is basically set up the same way as the one on the left. And so this is the number percentages of amino acids within carbonaceous chondrites. And I compared these numbers to the number percentages of amino acids in impact experiments. I wanted to see that the composition of amino acids in these experiments are actually adequately representing the amino acids that are found in meteorites. So as you can see, the gray, which is the impact experiments, is lining up quite well with the colors. And then on the right of the graph, non-heteroatoms, so the CH side chains, they're a little bit underrepresented, but it's very minuscule representation. And so that's good that these impact experiments are representing these amino acids. And so that way we can get a better idea of how these amino acids are reacting with these meteorites, how the pressures are reacting. And so that will give us a better idea to look at these experiments and analyze them. And so next slide. Okay, and so this is the results of the impact experiments. And so I took all of the data from my impact experiments and I put it into a Y-bell distribution. Actually, I had help from Dr. Remy Boulak, who made this wonderful distribution for me. And this is a function that starts at 0 and is basically the integrated form of my impact experiment data. And so the y-axis of this chart shows the probability at which amino acids will be destroyed at a certain pressure. And then the x-axis just shows those pressures. And so from this fit, we can see that CH side chains have a higher chance of survivability at higher pressures. And so what this means is that CH side chains are more likely to survive at pressures lower than 15.8 gigapascals. And then with linear, it's about 13.3 gigapascals. And so this is actually really exciting and really cool because all of this data was compiled from about 3 to 4 different authors. So if you look at all of this, it's really cool because we are able to put all this data into one trend and fit it that way. And so there's a larger trend of amino acid survivability being conserved over these impact experiments. So that's really exciting because that means that there is a chance of survivability based on the structural characteristics. And there's something that has to do with structure that imparts in the protection against the decomposition of these amino acids. And so that's something that should be investigated further, and I'm excited to look into the future as well. And so next slide, please. And so then I compared natural meteorite data to impact data and biology. And so as I mentioned earlier, I compiled data from non-carbonaceous and carbonaceous chondrites. And so I kind of separated them in this so that it would be easier to see. So carbonaceous is in pink and non-carbonaceous is in red. So as you can see from this again, the impact experiments in blue are again accounting for all natural meteorites, including non-carbonaceous and carbonaceous. And so this figure also includes the number percentages of amino acids in the body. And so I wanted to see if these percentages in our body were similar to those in meteorites, because not all amino acids are thought to have been brought by extraterrestrial objects, but there is a similarity to these compounds in the linear side chains, and so that can have an implication for the origin of life. There's not really similarity with the CH side chains or cyclic side chains either, which I did not include here on this graph, but it's a very interesting implication that this could be the reason why. And the next slide. But humans are not early biotic organisms. The concentrations of different amino acids in the body have changed over time, just on how we've, on our evolution and our metabolic processes, metabolic processes, sorry. And so it's very interesting that if you look at this phylogenetic tree, yes, thank you, Dr. Beeler, animals, we are up here. And so at the very bottom is our last universal common ancestor, and that's Luca. And so archaea comes first before animals. And so it would be really interesting to look at the composition of amino acids in ancient archaea to see how the composition of these amino acids compare to what is the composition in natural meteorites. So hopefully that will give us a better understanding of maybe a better idea of how amino acids might have been brought to Earth by these extraterrestrial objects, and maybe how they kind of developed into who we are. And so something else that I would like to do is just look further into these papers and report more amino acid concentrations for CV and CO chondrites. And then this was on my part. I did not put a acknowledgement slide. That was totally my fault. I got left out. But I would like to thank Dr. Remy Bullock for all of his help with the Y-bell distributions and the analysis of those. And then I would like to give a special thank you to Dr. Vanessa McCaffrey and Dr. Nicole Zellner for all the work that they have helped me do on this project, and all the work that we will do in the future with this project as well, which I'm super excited for. And then thank you to just the chemistry, biochemistry department, and the honors department as well. And then all of you for being here today. Thank you.
Well done, Hannah. We've still got a minute or two for questions if anyone would like to send one through the chat. Okay, we've got a quick question. What are the next steps?
The next steps for the project or the next steps for my life, like career-wise?
Let's go with both.
Okay, yeah. So in the summer, I'm hoping to work, well, I will be working with Dr. McCaffrey and Dr. Zellner, just furthering this project. I would like to hopefully get it published pretty soon. So that's something that I'm looking forward to. And then I will be going to Purdue University in the fall to get a PhD in medicinal chemistry.
Great. And this might take a longer time, but would you say that we are all extraterrestrial?
So San and I have actually discussed this. Yeah, we might be. You never know. But that's something that I'll definitely be looking into. So yes, San, we might be aliens. You never know.
Yeah, that is a deeper topic for another time. But well done and congratulations.
Yes, thank you very much, Hannah. Wonderful presentation.
Awesome.
Congratulations on your congratulations on your thesis award this morning.
Oh, thank you very much. Yeah,
recognized during the honors convocation, and which is a good reminder that we've seen several people who have been recognized at this morning's honors convocation already today. And so, if you have a chance, make sure you get a chance to look at the video. So, thank you, Hannah.
Awesome. Thank you.
Okay, so for our next presentation, we have Mary Beal, and Mary's faculty sponsor is Dr. Kevin Metz. Mary.
Hi, so I'm Mary. I'm a senior chemistry major, and I'll be presenting on my work with catalytic hydrogenation of oxyanions using transition metal carbon microspheres. Next slide, please. So oxyanions are a type of molecule that has a central atom surrounded by a certain amount of oxygen atoms. And a lot of them are emerging contaminants in the environment. And this is because they're found in a lot of fertilizers and rocket fuels. And their concentrations in the environment are increasing as our use of rocket fuels and fertilizers and other chemicals are also increasing. And many of these also have negative health effects. And they aren't currently, am I still talking? Sorry.
I can hear you fine.
So a lot of them still have negative health effects and aren't being removed from our wastewater while during treatment. And so our work is focused on reducing bromate, which is easy enough to reduce to get results, but also difficult so that it could be applied to different systems later. Next slide, please.
Looks like Mary just froze. We'll give her a few minutes. Maybe I just froze.
Sorry, my internet just gave out.
Mary, can you hear me?
I can. Can you hear me?
Yes, I can now hear you again. Okay.
Lovely.
Go ahead.
Okay. So current solutions for the reduction of oxyanions include electrochemical reduction, biological treatment methods, adsorption, membrane filtration, ion exchange, and catalytic hydrogenation. And so our lab focuses on catalytic hydrogenation. And so hydrogenation is the reaction of hydrogen with a different species, and the catalytic portion refers to the use of a catalyst. So this reaction is shown in the figure to the right. And so what happens is our bromate and hydrogen are adsorbed onto the catalyst, where they react, and one of the oxygens is stripped away from the bromate and added to the hydrogen, creating a species with one less oxygen and then also water. And this happens multiple times until at the end, all of the oxygen is stripped away, leaving just a bromide ion and water. And so bromide isn't harmful to the environment or to our health. And so reducing things to get down to this single atom ion is the goal. And so right now, a lot of catalysts are using platinum and palladium metals, which are very expensive and not earth abundant. And in order to make something that's economically viable to be applied to large scale and also be sustainable in the future is looking at alternative catalysts. Next slide, please. And so our goal is to create a catalyst using inexpensive earth-abundant metals on a carbon scaffolding that successfully reduce bromate to bromide. And so the metals that we're using to create these catalysts are listed on the right, and they are nickel, iron, copper, and cobalt. And these metals we are looking at because they're being researched in other catalysis applications, and so we thought to look at them here. Next slide, please. And so our first step is to make our catalyst, and this is our system to do this is shown in the figure. And so we do this using ultrasonic spray pyrolysis. And off to the left of the picture, out of frame, is a nitrogen gas tank, which is connected to an essential oil diffuser. And in our essential oil diffuser, which is on the left side of the picture, is our precursor solution. And in that solution consists of potassium dichloroacetate and different metal ions, depending on the metals that we want in our catalyst. And that diffuser makes the precursor solution into a mist, which is then carried by the nitrogen gas into our tube furnace in the middle. And in that tube furnace, all of the water evaporates essentially, which causes the solids to co-precipitate. And so this results in carbon, metal, and a potassium chloride salt co-precipitating into little spheres and being carried by the nitrogen gas into a system of bubblers. And in those bubblers, the potassium chloride dissolves, leaving porous carbon microspheres with metal nanoparticles embedded within them. Next slide, please. And so this is the scanning electron microscope image of a carbon microsphere. And for reference, so we do a lot of characterization on them. For reference, they are 2 to 4 micrometers in diameter, and about 50 of them could fit across the width of a piece of hair. So we also, through our characterization, discovered that nanoparticles are embedded within the catalyst instead of on the surface, so that there is carbon layer over top of the metal nanoparticles. And then also we determined that the metals are present in a 1-to-1 ratio, which is the same ratio that we put them in our precursor solution. So we determined that we could manipulate the ratio of the metals in the catalyst depending on our precursor solution. We also determined that the carbon is graphitic and that there's about 6 weight% of metal on the catalysts themselves. Next slide, please. So now that we have our catalysts, our next step is to actually use them and test them. So to use them, we set up the system in the picture. We put our catalyst and our bromate solution into a flask and evacuate the air out. and then we backfill that with hydrogen gas. Then we let that stir overnight under a hydrogen gas atmosphere, which is what the balloons are filled with. So the reaction that we hope is happening is on the right, and the final product is bromide, and that's what we measure after our reaction to determine if our catalyst worked. And so the thing you want to keep in mind is that high concentrations of bromide are good, because that means our oxyanion is gone now. Next slide, please. And so we started by testing all of our systems with palladium catalysts, just so that we have something to compare our alternatives to. And so all of our palladium catalysts reduce between 55 and 70% of our bromate to bromide. And so that's what we will be comparing our catalysts with. Next slide, please. And so we synthesized 6 different catalysts at first and tested them each in the way I just described. And our best results were with our nickel iron carbon microspheres, and that reduced about 8% of the bromate to bromide. And so our next steps were to look at ways to improve that system and optimize the performance of the catalyst. Next slide, please. And so we looked at 3 different ways to optimize this so far. The first thing we looked at was a pressurized hydrogen atmosphere. And so we did that using a PAR reactor, and that pressurizes the hydrogen gas going into the system, which theoretically would incorporate more into solution and result in more bromide as a product. And then we also looked at copper as a promoter metal. And so we made catalysts that were nickel iron copper carbon microspheres. And we did this because a lot of precious metal catalysts use copper as a promoter metal, so we thought to use it here. And we also used a new synthesis technique that had been used previously in the lab for something else. And so this happened by, we took a bare carbon microsphere, so one that we made without any metal ions in the precursor solution. And we soaked it in a tin bath for 30 minutes, where the tin coordinated onto the surface of the carbon microsphere. And then we soaked those carbon microspheres in a metal ion bath for 30 minutes, which caused metal nanoparticles to form on the surface. So there was no longer a carbon layer over top of the metals. And so say we wanted to make a palladium catalyst with the synthesis, we would make sure that second metal ion bath had palladium ions in them. Next slide, please. And so these are our optimization results for our nickel iron catalyst. And so the first column is just what we had at the beginning. Our high pressure reactions reduced about 3% of the bromate to bromide, and our copper as a promoter metal reduced about like 1.5%, and our new synthesis technique reduced about 5% of the bromate to bromide. So nothing was as good as our original nickel iron carbon microsphere catalyst. Next slide, please. And so overall, we can say that we did synthesize alternative catalysts, and they did reduce bromate to bromide, but their results were nowhere near that of the commercially available palladium on carbon or our palladium microspheres. So also our optimization efforts did not improve catalytic activity either. And so in the future, I'm going to be passing this on to new people who joined our lab this semester, so that's exciting. And I will be attending Texas A&M for graduate school in the fall. Next slide, please. And I'd just like to acknowledge everybody on the slide. Mets for dragging me into lab freshman year and giving me somewhere to do research. Dave for always like being there on the floor at 8 a.m. when all the professors didn't have 8 a.m. classes. And Sloan Schultz, he worked on this research with me for the past 3 years. And then Wayne State and Trinity for letting us use our instrumentation, and also for withdrawal of the funding. Next slide, please. And thank you to all of you for listening to my presentation. I can answer any questions.
Please share any questions you might have in the chat, everyone. Okay, why did the high pressure hydrogen synthesis not do as well as the atmospheric pressure syntheses?
So our high pressure optimization was actually the reaction conditions of the bromate to bromide reduction, but it worked better for our palladium control that we did. And the only thing that I can think of why it didn't work was that something happened where the stopper popped off or something, because if it worked for palladium to do better, it should work for our nickel iron catalyst. It might be that no one else really knew how to work the PAR hydrogenator as well either. So it's something that can be looked at by the newbies in lab. It's just how science goes.
Any other questions? Any plans to look at other oxyanions?
So our very beginning of our research, we started looking at chlorate and perchlorate, because perchlorate's kind of the main goal because it isn't removed in wastewater treatment and it messes with people's thyroids. And so we tried doing chlorate to work as a model for that, and we didn't get any results. And so that's when we switched to bromate. So our first step is trying to get all of our bromate results a little better, I think. But theoretically, the goal is to adapt it to harder systems.
One last question. I think we've got a minute yet. How prevalent are these pollutants in the environment?
I know nitrates are very prevalent because they're a really big component of fertilizers, and those have been used for ages. And then the perchlorate is an emerging contaminant, so it's not a huge issue yet, but it will be, especially since we are launching more rockets, and it's really prevalent in rocket fuel.
Great, thank you. I think we're just about out of time, but congratulations and best of luck at A&M.
Did Mary freeze up? Thank you very much, Mary. Great presentation. Terrific topic. I think we're ready to move on to our next presentation. There we go. Our next presentation will be given by Peter Philbrandt and Caitlin Piątkowski, and their faculty advisors are Dr. Craig Strew and Dr. Chris Robin. Peter and Caitlin.
Hi, everyone. My name is Peter Philbrandt.
And I'm Caitlin Piątkowski.
And today we will be discussing our ongoing research project of developing a nanobody to target the type 3 secretion system. Next slide, please.
It's well known that plants, including food crops, can be killed and damaged through several mechanisms, such as bacterial infections. On this slide, we can see two different plants that are common crops raised for human consumption, and both of whom have experienced damage due to bacterial infections. Rice and tomatoes are also both targeted by bacterial species that use the same mechanism. The bacteria which target these plants for the rice is Xanthomonas oryzae, PV oryzae, shown on the left, and on the right is Pseudomonas syringae, which infects the tomato plants. And our projects aim to develop new antibiotics to halt the infection of the plants from our target bacteria. And both of us are using the same developmental techniques and concepts to target different bacteria. Next slide, please.
So Xanthomonas oryzae and Pseudomonas syringae, they are both gram-negative bacteria. So this means that they have two layers of cell membranes, and this makes them difficult targets for common antibacterial techniques. And however, our bacteria, they also operate using a type 3 secretion system, or T3SS, which is pictured here. And as you can see, the bacterium build from the inside out, so they create this P-less structure that reaches across both membranes and spans the plant cell wall. And so the resulting protein structure is the type 3 secretion system. And this allows the bacteria Xanthomonas oryzae and Pseudomonas syringae to infect their host cells. And the type 3 secretion system is essentially a transport tunnel, and it attaches to the host cell and transports the bacteria's effector proteins through to the cytoplasm. Next slide, please.
Yeah, these extracellular protein structures are large proteins composed of several subunits that must be synthesized and arranged in the correct order by the cell. So in order to shut off the infection mechanism, we aim to insert a small molecule into the structure to disrupt the cell's formation of the type 3 secretion system. And by doing this, the T3SS will no longer be able to form in a way efficiently to infect the host cells. And for each of our target cells, we've determined the subunit proteins to be HPA1 for the Xanthomonas oryzae and the HRPW for the Pseudomonas syringae. And these small molecules to be developed will be nanobodies. And those will be designed to target and shut down these respective effector protein translocations. Next slide, please.
And as Caitlin mentioned on the previous slide, the small molecules we will use to attack our target proteins are nanobodies. And so nanobodies are small protein fragments of antibodies. And on this slide, we can see the structural relationship between antibodies, other smaller antibody derivatives, and nanobodies as well. And antibodies are molecules composed entirely of proteins that have several distinct regions. And so the region that we are most interested in is the CDRs, or complementary determining regions, and they are located on the end of the antibody's variable region. And so this region is responsible for binding to the target antigen due to its precise structure and affinity for the target antigen. And as the antibody derivatives become smaller and smaller, going across the screen left to right, we can see that in the nanobody structure, the complementary determining region is the only region that is conserved. And so we only need this function of the antibody to disrupt the type 3 secretion system's formation. So therefore, this nanobody will serve our purposes. Next slide, please.
To develop these nanobodies, we're going to use a method called yeast cell surface display. In the last year, we purchased a library of yeast cells that had been genetically modified to display proteins the size of nanobodies on their surface. In the slide, you can see as well that each cell displays the same protein over its surface of its cell, which is made up of two subunit proteins connected with a disulfide bridge. The nanobody will be connected to the Aga2 structure with fluorescent tags on its end. This has allowed us to develop a cell library in which each cell displays its own nanobodies on its surface, and by using this concept, we can use processes that we'll describe in later slides to select cells from our library to attack and attach to our target proteins. Next slide, please.
And along with the cell surface display, we also use a technique called directed evolution. And as we can see from the cartoon of Charles Darwin in the test tube on the left, directed evolution closely mimics the concepts of evolution outlined by Darwin, but in a laboratory as opposed to in nature. And in directed evolution, they use cycles of several steps to select and enhance cells based on their physical and genetic characteristics. And so in directed evolution, we begin with a library of cells or similar genes, as we can see in the figure. And the genes are then translated into proteins that we can use to select precise cells from the whole library. And once these cells and their corresponding proteins have been selected, they can be replicated to build up a new library and diversified with mutations to create similar but different offsprings. And from here on, the cycle can be repeated over and over again until the desired physical characteristics have been found. And using this technique, we can use our yeast cell library to select cells that have the correct structure and the correct makeup to attach to our targeted proteins. Next slide, please.
Yeah, so of the directed evolution process, one of the most important steps is the selection of the cells, because without selecting the cells we wouldn't be able to advance in the cycle or determine which cells can actually bind to our target proteins. So shown in this slide is one of the selection methods that we use called MAX, or magnetic activated cell sorting. So in MAX, cells from the library are mixed with metal beads that are bound to our target antigens. So for Xanthomonas oryzae, the HPA1, and for Pseudomonas syringae, the HRPW, that are bound to the bead via biotin strip avidin bond. And when the cells and the beads are mixed together, the cells displaying the protein complementary to the target protein will bind to the antigen. And then through this binding, the cells with our desired protein will now be linked to the metal bead and suspended between the magnet. And the library will then be eluted while in the presence of the magnet to elute all the yeast cells that didn't bind to the metal beads. And then the remaining cells in the column will be those with our desired proteins, and we'll elute them separately when they're removed from the magnetic field. Next slide, please.
And so here on this slide, we can see the importance of our selection techniques. And so our total library is roughly 2.5 billion cells large. And we're looking for the few cells in this library that can actually bind to our targeted protein. So essentially, we are attempting to find a needle in a haystack, and we're going to need clever and effective techniques to achieve this. So this means that the methods we use, they're going to have to be efficient and effective to make sure that we get all the cells in this population of 2.5 billion cells. And so on the slide, the plated cells that we see are from a serial dilution that we did on our total yeast library. And so a small sample is taken from the whole yeast library and made into several different dilutions that were then plated. And as we can see, the number of bacteria colonies on each plate decreases drastically going from the left to right. And so when we compare the small sample of cells that have been plated, we can mathematically determine the incredibly large number of cells that exist in our library, which is 2.45 billion cells. Next slide, please.
Yeah, so as Peter was saying, using those dilutions, we were able to confirm our library size. But after this, we were still unsure whether or not our yeast cells were displaying nanobodies on their surface. So to determine this, we used a method called fluorescent activated cell sorting, or FACS, which is a process by which cells are flowed down and dripped down one by one through this fluorescent laser here, which will sort the cells based on whether or not they contain fluorescent tags, which are associated with the nanobodies. So here on the right is data we actually got from our FACS run. The y-axis shows the cell count, and the x-axis shows the fluorescent activity. So the higher the fluorescent activity, the more higher your chances of nanobodies were. So the darker region on the right shows our cutoff point to where we were confident that our cells were containing nanobodies. And it doesn't look like a lot, but with a library size of 2.5 billion, that small area still gives us hundreds of thousands of displaying nanobodies to potentially bind to our targets. Next slide, please. And in order to select for our cells, we also must create an antigen to coat the beads in for our MAX. And to do this, we began by buying HPA1 DNA that was genetically modified with acanthamycin resistance. So we took this DNA and transformed it into DH5 alpha cells, shown in the first two plates, which are able to synthesize an abundance of bacterial DNA. And then these plates show the colonies we grew. The second place was a control created with just kanamycin and no bacterial spread, in order to prove that all of the colonies showed in the first picture were all colonies of the HPA1 bacterial colonies with the DNA in them. And so once we had enough HPA1 DNA, we transformed that into the BL21 cells, which are the third and fourth plates, which are able to synthesize and amplify proteins. So now that we have synthesized an abundance of HPA1 proteins, we will be able to attach the proteins to a bead for selection.
And moving on to our future work, we will attach the HPA1 protein synthesized by the BL21 cells to our magnetic beads and begin rounds of selections of yeast cells to find the nanobodies capable of targeting the HPA1 protein. Next slide, please. And so lastly, we just like to thank the FIRSTCA program and committee, Dr. Strew and Dr. Roman, the chemistry department, Dave Carey, our lab mates, and the test year lab of the University of Michigan. Thank you.
Thank you.
Thank you both. Well done. Looks like we've got just about 2 minutes left. If there are any questions, please send them through the chat. First question, how long will each evolution session take?
It kind of actually depends on the library, because we actually did one round of selection already, and since we had such a large library to begin with, it took probably, I think I was there for about 7 hours one night doing it, but each time it starts narrowing down to smaller and smaller cells that you actually have to do, so it starts getting to be slower or less and less time each time.
Okay. The next question, why are there so few nanobodies displayed on the surface of yeast during FACS?
Well, that's actually because when we get the yeast cell library, they do a process to get the DNA into the yeast cell called electroporation, and it's super inefficient, sorry. But that wasn't anything that we did.
Yeah, I think we're probably close to out of time. Thank you both very much. Well done.
Thank you.
Thank you very much, both Peter and Caitlin. We have just a couple minutes. I want to let more people arrive. I see people are coming in. So I'll take this opportunity to thank everyone and congratulate all of our presenters today. Lots of great presentations. We have one more to go. Emily is getting ready to present. And so for all the time and effort that you've put into all the research that you've done over the last several years, great accomplishment to everyone. It is 3:30. It looks like we have a great complement of people. So I will introduce our final speaker of the afternoon, Emily Eggenberger, whose faculty sponsor is Professor Andrew Grossman. Emily.
Thank you very much. Thank you everybody for coming, and I hope you enjoy my thesis entitled From Duck and Cover to Active Shooter Drills, the Consequences of Emergency Planning on Our Nation's Children. Imagine you're in 4th grade again. You're practicing long division, reading books like Mr. Popper's Penguins, and learning about the 3 branches of government. You love art class, and your favorite thing to do at recess is swing on the playset while you chat with all your friends. You look forward to dance lessons or soccer practice after school, and when the day is done, you love nothing more than a game of Foursquare in your driveway with all your neighborhood pals. Life as an 8-year-old is free, fun, and innocent, until one day it isn't. Huddled against the back wall of your classroom in the dark, your teacher tries desperately to quiet the terrified whimpers of your classmates as the bursts of gunfire and sounds of screaming grow ever closer. You've been practicing for a day like this since before you could even read, but you never thought it would actually come. You hug your knees to your chest to make yourself as small as possible, sitting shoulder to shoulder with every student in your class. You don't want to cry in front of your friends, but the silent tears come rolling down your cheeks as you cower in fear, waiting, begging for it all to be over. Hypothetical or not, this is the horrific reality of the America our children are living in, and it is sadly not all that different from an America we've known before. During the Cold War period, American school children suffered a similar trauma, ducking into classrooms and bunkers, covering their heads, and praying to make it home alive. Instead of being terrified of the possibility that they may be shot in the middle of math class, children in the 50s and 60s were terrified of the possibility for complete and total nuclear annihilation, where not only would they be lucky to survive an attack, they'd be lucky if their remains were even identifiable. Instead of gunshots in the hall, it is the air raid siren that startles these children into action. If they're fortunate enough, their school would have a fallout bunker and they could quickly proceed to the basement towards safety. If not, it was up to the shelter of their desks and their ability to duck and cover to save them. Here too is where the fear and worry set in, along with that same hushed whimpering and those same silent tears as the excruciating wait for death draws on. Sound familiar? Throughout history, the United States has employed similar methods of emergency procedures to prepare students for potential threats. In this particular case, I focused on similarities between duck and cover and active shooter drills in schools. These drills are designed to control fear and mitigate panic by teaching easy steps to follow in order to ensure survival in the event of a dangerous situation. By presenting the nuclear situation as being easily thwarted via a simple duck and cover technique, or the active shooter danger being quickly dissolved with a couple lockdown procedures, the threats become a little less terrifying. Similarly, by repetitively practicing what to do in the case of either of these emergencies, in theory, panic will be minimized in the event that such an emergency would ever actually occur. However, I argue that these drills have only served to perpetuate fear as they have forced children to participate in anxiety-inducing and sometimes chaotic drills. Before getting into the thick of my analysis, I will start with some quick definitions and an exceptionally brief historical overview. On this first slide here, we have the duck and cover drill, a drill during which students are instructed to hurriedly duck beneath their desks and cover their heads with their hands to brace for a nuclear attack. In response to the Soviet threat during the Cold War era, the Civil Defense Administration produced many public service announcements, the most relevant to our topic being the film entitled Bert the Turtle, which ushered in the duck and cover drills that would be practiced in schools for over a decade. Constantly bombarded with information about the escalation of the nuclear threat, children of the Cold War received mixed messages. On the one hand, they were made to believe that nuclear war was easily survivable. But on the other, they were told that nuclear war was inevitable, and perhaps even that the government was helpless to save them from such a fate. Just as there was fear, public policy response, and training in civil defense for nuclear war, today we find ourselves faced with a new threat and another generation of people that will be traumatized by the preparation for such events. The Columbine High School Massacre of 1999 is commonly thought of as the event that ushered in the current mass era of mass shootings in schools. And with it came the employment of hard and soft lockdown and ALICE drills to prepare students for this harsh reality. First, we have the hard lockdown drill, where doors are locked, lights are turned off, and students are sheltered in their classrooms, specifically in areas that are not visible from the door. Next, we have the soft lockdown drill, one in which lights are turned off and doors are locked, but teachers are otherwise allowed to continue conducting class as normal. However, students are not permitted to leave the classroom. Next, we have the ALICE drill, a new one, which stands for Alert, Lockdown, Inform, Counter, and Evacuate. On this next slide, we can see the approach where teachers and students have the option, next slide please, to shelter in place, run, or fight back in the event of an active shooter situation. These drills can be incredibly realistic, as you can see, and very frightening. The practice of developing precautionary protocols to create an air of safety and, more importantly, to avoid the problem of panic is not foreign, nor is it exclusive to schools. In many instances across many aspects of life, we feel comforted by the idea that we are safe from harm. When we check our bags before heading into a concert venue, when we walk through a metal detector before getting on a plane, when we see bright exit signs with clear evacuation paths at the movie theater. In all of these scenarios, we feel confident that we are protected from those who try to hurt us. Security theater, a term originally coined by security expert Bill Schneier, next slide please, describes the way in which various entities invest in countermeasures intended to provide the feeling of improved security while doing little or nothing to actually achieve this improved security. Schneier makes the claim that you can feel secure even though you're not, and you can be secure even though you don't feel it. And he says there are two ways to make people feel more secure. The first is to improve security and hope that people notice, and the second is to make people feel secure without actually improving security and hope that they don't notice. Not only is this the principle that has guided the drills that I have examined throughout my thesis, but it is the principle that encompassed the entire Cold War era. We know that after a nuclear attack, the world would never be the same as it once was, and more importantly, we know that surviving would be laborious and difficult. However, by acting as though the U.S. was well prepared for the potential disaster, citizens remained mostly calm. So with that, the question still stands. Do these drills successfully mitigate panic while controlling fear? Everyone knows that ducking and covering under a desk wouldn't have saved a student from the detonation of a nuclear warhead. And in the same sense, just as many students have died in school shootings since the implementation of lockdown drills as they did before. In fact, the biggest school shootings have occurred since the implementation of lockdown drills and ALICE drills. But it is not the true purpose of these drills to save lives. Instead, it is to calm fears and develop protocols that minimize panic and chaos in the event of a dangerous situation. Because fear is what drives people to seek help and listen to advice. But panic creates an unruly, unpredictable, and sometimes even an apathetic population. An unintended consequence of these drills has been the severe increase in anxiety in children who actively participate. And sometimes this anxiety remains even into adulthood. Studies show that by the end of the 1950s, 60% of interviewed children reported having experienced nightmares about nuclear war. By the end of the following decade, 44% of children surveyed predicted a nuclear attack. By 1979, 70% of interviewees were absolutely sure of an attack. Meanwhile, in the present day, it's been shown that the active shooter drills in schools are correlated with a 42% increase in anxiety and stress and a 39% increase in depression among those in the school community, including students, teachers, and parents based on their social media posts. Meanwhile, qualitative anecdotal evidence is even more hard-hitting. When I first presented this thesis for my classmates in my senior capstone, I was met with stories from nearly every single student that reflected my experiences growing up in the area of mass shootings. Stories from my fellow students making mental escape routes for each and every classroom they entered. Stories of panic being triggered by the sound of someone popping open a bag of chips. Stories of teachers advising students to play dead or hide in their lockers should they ever end up caught in a hall during a shooting. My thesis advisor, Professor Grossman, actually taught our capstone, and I recall him looking around in bewilderment as he admitted that he'd had no idea the psychological trauma response that was present in his students, nor had he any idea that the fear my generation has toward active shootings was so comparable to that his generation has toward nuclear disaster. These generations have both been faced with terrifying realities as they have been confronted with their own mortality via these drills and impending dangers. But sometimes the intensity of these preparatory procedures can become far too much to bear, to the point where it can be truly traumatizing. During the Cold War era, for example, students in large urban areas were often issued dog tags to be worn daily so their parents would be able to identify their bodies. While today, students are being subjected to hyper-realistic drills, some of which are even made to appear as if they are real. Even in younger grades, students are being taught how to build forts to protect themselves from active shooters, all while learning words like barricade and practicing morbid nursery rhymes like the one you see here to remind them what to do in the event of a real lockdown. In taking up these intense practices, we may be creating a problem that is even worse than severe anxiety. Instead of instilling pure panic in the minds of American citizens, have these preparatory procedures caused some to cross the threshold into mere apathy? Has a drill officially gone too far when it has created indifference in a population of people who are so hopeless they no longer care if they live or die? During the Cold War era, many older students and adults joked about the nuclear danger, saying that rather than abide by faint attempts at survival when they saw the bright flash, they'd run outside towards the blast and hope for an immediate death. An instant death was far preferable to the alternative in which they'd have been forced to suffer through a nuclear apocalypse, but all jokes aside, we have a serious problem when a population would rather surrender to their deaths or worse, act on their own instincts instead of abiding by protocols, for it undoes the very order that these protocols have strived to put in place. With all this in mind, is it so unfair to argue that these emergency policies do not successfully manage fear and keep insanity at bay, but instead only perpetuate such tendencies further? Indeed, many adults have nightmares to this day of nuclear devastation, while news stories of frantic stampedes triggered by backfiring cars, for example, plague news outlets. Are we creating a country of traumatized citizens? Well, so what? The world is a traumatizing place, big deal, those kids will get over it, and more importantly, painful and traumatizing as these drills may be, so long as the threat is active, duck and cover and lockdown drills are inarguably necessary. However, I contend strongly with the idea that our children should simply toughen up. Children deserve a childhood of innocence and freedom where their biggest responsibility is to clean off the kitchen table at night and turn in a couple pages of homework. Why is it acceptable that the burden of saving their own lives from the fire of a guy with a gun who shouldered their science class fall onto the shoulders of children? Why are we asking that our most vulnerable population take on the weight of preparing for their own deaths? And why are we asking people who are frequently not even old enough to vote, let alone drive or even serve in the military, to sacrifice their lives instead of demanding policy change? At the very least, it's important that a federal policy be enacted to ensure that all schools are following similar protocols. Leaving literal life and death decisions up to inexperienced school boards and administrators is irresponsible and dangerous. When all schools are not following a universal standard of procedure, how can we be sure that our children are properly protected? Fire and natural disaster drills have the same general setup throughout schools and even the rest of society. There's no reason why active shooter drills shouldn't as well. For now, of course, we don't have a wide-sweeping national policy. Therefore, it is important to ask, is flawed emergency planning better than none at all? What happens when we are not prepared for a dangerous situation? In 2018, we saw firsthand in Hawaii the chaos that can ensue when emergency protocols are not established. Is there a benefit to maintaining training for such events, even if that training is helpless to actually save lives? While the government's fear of panic creates policy that may be useful, it can also create long-term psychological trauma in the minds of those who practice it. While training should be maintained in order to ensure emergency preparedness for all Americans, its logistics may need to be seriously reconsidered in order to minimize adverse effects in those who partake in the exercises. Thank you so much for listening, and special thank you as well to my faculty advisor, Dr. Grossman, who's been fantastic, as well as my other two committee members, Dr. Drew Christopher and Dr. Bill Rose. Thank you, everybody.
Thank you, Emily. Very well done. We've got a couple of minutes left for questions, so folks, please send those along through the chat. Okay, Jennifer would like to know what got you interested in this topic.
That's a great question. So actually, it was originally I was wanting to do a topic studying whether a nuclear weapon would be used in the next century, given that the generation who was put through this training and everything is starting to grow old and leave office. And while I was talking to Professor Grossman about this, he let me know that another student was currently doing a thesis that was very similar to that. So we sat and brainstormed for a while before we figured out that I had started talking about how terrifying school shooting drills were to my generation, and how I had noticed that my generation was very active against gun control, starting March for Our Lives, things like that. We really seemed to take a stand on those issues more than other generations have. And Professor Grossman and I drew the conclusion that it was incredibly similar, the stance that his generation has against nuclear weapons, to the stance that my generation has against the shooting threat. And so it was that moment when we kind of had an aha sitting in his office, and came up with this idea for the thesis. And it's been incredibly interesting to continue to research, especially learning things about security theater and the true reasons for these protocols are not necessarily to save everybody's lives.
Now, Eddie mentioned he did not know about the dog tags that you mentioned, and as one who is old enough to have remembered hiding under my desk in elementary school, and not understanding the ridiculousness of that, I did not know about the dog tag feature. We didn't have that, but.
Yeah, I don't remember where it was that I found that little factoid, but it was one that I was like, oh, like that is so morbid. I can't even imagine walking to school with that around my neck, knowing the purpose of it. And maybe those students didn't know the purpose of it if they were young enough. But yeah, that was a fact that even when condensing my thesis into this small presentation, I knew I couldn't leave it out. It was a shocker right there.
Well, Emily, thank you very much for that presentation. It was terrific. And so Emily's is our last presentation for the afternoon for this forum. Thanks to everyone for attending the talks and for also presenting the talks. There are, I believe, Mike, do you know, are there still a couple for?
Yeah, a couple of the forums go until 4:15.
Yeah, so if you have the time, jump on over to one of the other forums. And thank you again, and I hope everyone has a great day.
Thanks all.
Thank you.
Bye.